Three of the biggest crisp brands in the world develop their product in ways you'd never think are even possible. Every ridge and every golden layer is engineered to hit differently, from the seasoning that clings to a Dorito to the airy snap of a Cheeto and the fragile bite of a Ritz cracker. In this video, we uncover how these iconic snacks are built for flavor and the kind of crunch people recognize instantly. Orange seasoning dust hits the hot tortilla chips inside a rotating drum, coating every moving triangle in a dry, bright layer. The drum turns at an angle, lifting the chips up its inner wall and letting them fall back through a fine cloud of seasoning. The chips are already fried and crisp at this point. They are still warm enough for the seasoning to cling, but cool enough that the coating does not clump into wet patches. A metering system feeds the seasoning powder through a controlled auger. Another line may add a very fine mist of oil before or during seasoning. The oil helps the powder attach to the chip surface. The powder contains cheese flavor, spices, salt, acidity components, color, and other dry ingredients depending on the Doritos variety being produced. The chips do not remain still while coating happens. They tumble constantly. Each triangle flips, slides, and collides with the others. One side catches seasoning, then the other. The rough fried surface gives the powder tiny edges and pores to grip. This seasoning stage is one of the last transformations, but the chip begins much earlier as corn. Whole corn kernels enter the production system and pass through cleaning equipment. Vibrating screens remove broken pieces, dust, and oversized material. Air separators pull away lighter fragments. Magnets capture small metal particles before the grain continues. The cleaned corn moves into a cooking system. Water and lime are added to the corn in a process that softens the kernel structure and prepares it for grinding. The lime-treated cooking liquid changes the corn's outer layer and improves how the masa will form later. The corn cooks in large vessels under controlled heat. The kernels absorb water. Their outer holes loosen. The interior softens but does not turn into paste. The cooking time and temperature must be balanced so the kernels become grindable while still producing a dough strong enough for sheeting. After cooking, the corn rests in steeping tanks. During steeping, the kernels continue hydrating. Moisture moves deeper into the grain. The texture becomes more uniform from the outer surface to the center. This resting step is important because unevenly hydrated corn would grind into rough, inconsistent masa. The steeped corn is then washed. Excess lime and loosened hull material are removed as water passes over and around the kernels. The washed corn drains before grinding. It is now softer, heavier, and ready to become masa. Grinding turns the cooked corn into a dough. The kernels pass between stones, plates, or grinding surfaces that crush them into a moist corn mass. The grinding must create the right particle structure. Too coarse, and the dough tears during sheeting. Too fine, and the chip can become dense or sticky. The resulting masa is warm, moist, and slightly coarse. It has the aroma and texture of cooked corn. The mass moves through mixers or holding equipment that evens out moisture and texture. Small adjustments may be made so the dough sheets correctly. The masa enters a sheeting machine. Two large rollers pull the dough into a flat band. The roll gap controls thickness. The sheet must be thin enough to fry into a crisp chip, but thick enough to survive cutting, toasting, transfer, and frying without breaking. The surface becomes smoother as the masa passes between the rollers. It forms a continuous sheet moving forward on a belt. If the sheet is too wet, it sticks. If it is too dry, it cracks at the edges. Moisture control is constant throughout the forming line. A cutting roller presses triangular shapes into the moving sheet. The cutter creates the Doritos chip outline. The remaining web around the triangles separates from the cut pieces and can be redirected back into the dough system in controlled amounts. The fresh triangles are still raw masa. They are pale, soft, and flexible. They do not yet have the crisp structure of a chip. They move into an oven or toasting section before frying. The toasting stage partially cooks and firms the triangular pieces. Heat removes some surface moisture and sets the shape. The chips become strong enough to enter the fryer without folding or dissolving into the oil. Their edges dry slightly, while the centers remain moist enough to puff during frying. After toasting, the chips may pass through an equilibration stage. This allows moisture inside each triangle to even out. If the outside is too dry and the inside too wet, frying can create blistering or uneven texture. A short resting period helps each piece fry more predictably. The chips then enter the fryer. Hot oil surrounds the triangular pieces as they move through the fryer on a conveyor. Moisture inside the masa flashes into steam. Tiny bubbles push outward through the chip structure. The chip becomes lighter as water leaves, and oil heat sets the starch network. The surface changes from pale corn dough to golden, crisp tortilla chip. The edges curl slightly. Small bubbles and blisters form across the surface. These irregularities give the chip its crunch and help seasoning cling later. The fryer temperature and dwell time control texture. If the chips move too quickly, they remain tough and damp. If they stay too long, they darken and become brittle or burnt. The oil circulates continuously, and filtration systems remove small crumbs that break away during frying. At the fryer exit, the chips rise from the oil on a draining conveyor. Excess oil falls back through the belt. The chips are crisp but still hot. They move through a cooling and oil draining section where air passes around them and the surface stabilizes. This is where the chips become ready for seasoning. They must carry enough surface oil for powder adhesion, but not so much that they feel greasy or cause seasoning to cake. The chip temperature must also be correct. Very hot chips can cause seasoning volatiles to flash off too quickly. Cold chips may not hold the powder as evenly. Before entering the seasoning drum, the chips pass through distribution equipment. The flow is spread into an even curtain, so the seasoning system receives a steady amount of product. This helps keep the coating level consistent from the beginning of the run to the end. Inside the seasoning drum, the chips tumble while powder is fed in. The rotation angle moves them forward gradually. Seasoning falls onto the rolling bed of chips. The sound is dry and constant. Chips sliding, tapping, and rattling inside the metal cylinder. For nacho cheese, the powder creates the familiar orange-red surface. For Cool Ranch, a lighter seasoning blend coats the chip with visible green and darker specks. For spicier varieties, color and chili components create a deeper, more intense surface. The same tumbler can handle different recipes when cleaned and set up for the next flavor. The seasoned chips exit the drum and travel on conveyors toward inspection. Broken pieces and excess small fragments can be separated through screens. Airflow may remove loose powder and light fines. The product stream becomes more uniform before weighing. Vision systems can check color distribution, chip shape, and dark or burned pieces. Metal detectors scan the flow. Defective material is removed automatically. The accepted chips move into large overhead hoppers above the packaging machines. The hoppers must handle the chips gently. Doritos are crisp and thin, so sharp drops would create excessive breakage. Sloped surfaces, controlled gates, and short drop distances help maintain chip shape as they feed into the weighers. Multi-head weighers portion the chips into bags. The chips travel along vibrating feed channels into small weighing buckets. Each bucket holds a different amount. The control system selects a combination of buckets that equals the target bag weight as closely as possible. When the correct combination is chosen, the selected buckets open. Chips fall into a timing funnel above the bagger. The drop must be controlled so the chips land cleanly without shattering. The bag begins as a roll of printed flexible film. The film unwinds and passes over a forming collar. The flat film bends around the collar and becomes a vertical tube. A heat seal closes the back seam. Cornmeal bursts from the extruder, die as a hot, expanding rope, then snaps into short curls almost instantly. The dough inside the barrel is under heat, pressure, and mechanical force. As it exits the small die opening, the pressure drops suddenly. Moisture trapped in the cooked. Cornmeal flashes into steam. The soft material expands outward, creating a porous puff with an irregular shape. A rotating knife cuts the stream into short pieces as fast as it emerges. This is the central transformation in Cheetos production. Doritos are made from a sheet of corn masa cut into flat triangles. Cheetos are formed by extrusion. The shape is not stamped from a sheet. It is pushed through a die, expanded by pressure release, and cut into pieces while still hot and soft. The process begins with milled corn. Cornmeal arrives at the production system as a dry, granular ingredient. It is not as fine as flour and not as coarse as whole cracked corn. Its particle size must be controlled so it hydrates evenly, cooks correctly, and expands through the extruder without clogging or tearing. The cornmeal passes through screening equipment. Oversized particles are separated. Fine dust is reduced. Magnets remove tiny metal fragments from the ingredient stream. The cleaned cornmeal enters storage bins above the mixing and extrusion line. A feeder meters the cornmeal into the preconditioning system. Water is added in a controlled amount. The water does not turn the cornmeal into a flowing batter. It creates a damp, crumbly feed that can be cooked by heat and pressure. The moisture level is critical. Too much water makes the extruded puff collapse or become dense. Too little water prevents proper expansion. Inside the preconditioner, rotating paddles mix the water into the cornmeal. Steam may be added to begin heating the starch. The particles soften slightly as they absorb moisture. The mixture becomes more uniform before entering the extruder. The extruder contains a long metal barrel with 1 or 2 rotating screws inside. The screws grip the moistened cornmeal and push it forward. As the material travels along the barrel, it is compressed, heated, and sheared. The screw flights knead the mixture continuously, turning dry granules into a cooked corn paste. Heat comes from friction, steam, and heated barrel zones. Pressure builds as the paste approaches the die. Starch in the cornmeal gelatinizes, forming a plastic mass that can expand when released. The material is dense inside the extruder, but it contains the moisture that will create the puff structure. At the die plate, the cooked corn paste is forced through small openings. The opening shape, pressure, moisture, and knife speed determine the final form. For classic crunchy Cheetos, the pieces emerge as irregular curls and sticks. For puffed styles, the expansion is larger and the texture becomes lighter. The material expands the moment it leaves the die. The surface roughens. The inside becomes filled with air pockets. Each piece twists slightly because the flow is uneven, and the cutting blade interrupts the stream repeatedly. This gives Cheetos their random curled shapes rather than identical, molded forms. Fresh extruded pieces are warm, pale, and fragile. They have expanded, but they are not finished. They still need heat treatment to develop crispness and reduce moisture. For crunchy Cheetos, the pieces move toward a fryer. They enter hot oil on a conveyor or controlled feed system. The oil surrounds each piece, driving off remaining moisture and setting the porous structure. The pale corn puffs turn darker and firmer as they fry. The fryer must keep oil temperature steady. If the oil is too cool, the pieces absorb too much oil and become heavy. If it is too hot, the outside darkens before the inside becomes properly crisp. The pieces move through the oil for a controlled time, then rise out on a draining belt. Excess oil falls away through the open conveyor. The pieces continue through a short, cooling and draining zone. their texture becomes harder and more brittle as the surface stabilizes. For baked Cheetos-style products, the extruded pieces take a different route. They pass through an oven instead of a fryer. Hot air removes moisture and firms the structure. The pieces become crisp through drying and baking rather than oil frying. The equipment changes, but the basic sequence remains extrusion, expansion, heat setting, seasoning, and packaging. After frying or baking, the plain corn pieces are still not recognizable as finished Cheetos. They are light yellow, crisp, and porous, but they do not yet carry the orange cheese coating. The seasoning system prepares the coating in a separate feed area. Cheese powder, salt, flavor ingredients, color components, and other dry seasonings are blended into a uniform powder. The powder must flow smoothly through hoppers and augers without forming clumps. A small amount of oil is often applied to the hot corn pieces before or during seasoning. The oil acts as an adhesive. Without it, the powder would slide off the dry surface and collect at the bottom of the equipment. With it, the powder grips the rough pores and ridges of each piece. The Cheetos enter a rotating seasoning drum. The drum is angled, so product gradually travels from one end to the other while tumbling. Inside, the pieces roll, lift, fall, and rub against one another. This motion exposes every surface to the seasoning stream. An auger or vibratory feeder meters the orange cheese powder into the drum. The powder falls onto the moving bed of puffs. Oil-coated surfaces capture it immediately. As the pieces tumble, the powder spreads across ridges, hollow spots, cracks, and curled edges. The color develops quickly. Pale corn pieces become bright orange. The uneven surface of each puff holds more seasoning than a smooth snack would. The coating collects in small pockets and along rough raised areas, giving the finished product its intense appearance. The drum speed is carefully controlled. Too gentle, and the seasoning remains uneven. Too aggressive, and the fragile pieces break into crumbs. The goal is a consistent coating while preserving the puffed shape. At the drum exit, the seasoned Cheetos fall onto a conveyor. Loose excess powder and small broken fragments may be separated through screening. Airflow can lift away light dust. The accepted pieces continue toward inspection and packaging. Inspection systems examine the product stream. Cameras can check color intensity, dark pieces, pale under-seasoned pieces, and obvious defects. Metal detection scans the flow before the snack enters packaging hoppers. Broken finds are removed so the bag contains mostly intact pieces. The seasoned Cheetos enter overhead holding bins. These bins feed the packaging machines while protecting the pieces from crushing. The snack is light and irregular, so the hopper surfaces are shaped to prevent bridging, where product sticks in place instead of flowing downward. From the bins, Cheetos move onto multi-head weighers. Vibrating trays feed portions into small buckets. Each bucket contains a different weight of product. The control system selects a combination of buckets that adds up to the target bag weight. The selected buckets open together. The measured Cheetos fall into a timing funnel. The drop must be managed carefully because the pieces are brittle. Long drops or hard impacts would create excessive breakage and dust. The bagging machine starts with printed flexible film unwinding from a roll. The film passes over rollers that control tension. It then wraps around a forming tube, turning from a flat sheet into a vertical cylinder. A heated sealing unit closes the back seam. Before the snack enters, the bag may be flushed with nitrogen. This reduces oxygen inside the pack and creates a cushion around the product. The trapped gas also helps protect the irregular curls from being crushed during handling. The weighed Cheetos drop through the forming tube into the open bag. Horizontal sealing jaws close below and above the product. One seal becomes the top of the filled bag, while the next becomes the bottom of the following bag. A cutter separates each finished package from the continuous film. The finished bag has a pillow-like shape. It is not packed tightly around the snack. The extra space helps protect the puffed pieces and preserves their crispness. Each bag moves through check weighing. A bag outside the correct range is rejected. Vision systems inspect print registration, seal position, date code placement, and bag shape. Any package with a weak seal, missing code, damaged film, or incorrect weight leaves the main line. Accepted bags continue to case packing. Conveyors guide them into lanes and arrange them into groups. Because bags are flexible and filled with air, the packing machine must compress them only enough to fit the case without crushing the contents. Corrugated cases are opened from flat blanks or preformed sleeves. Groups of bags slide into the case in a programmed pattern. The flaps fold inward. Adhesive or tape seals the case shut. Compression belts hold the case square until the closure is secure. A thin spray of oil lands on the hot cracker surface, and fine salt crystals settle into the tiny dimples before the cracker has fully cooled. This final surface treatment gives a Ritz cracker its smooth golden shine and sharp salty finish. The cracker is already baked, already crisp, and already round, but the coating makes the surface feel richer and helps the salt grip instead of sliding away. The oil is applied in a controlled mist. Too little leaves a dry, pale finish. Too much makes the cracker heavy and greasy. The salt follows through a separate applicator. A rotating drum or vibrating feeder releases a steady curtain of fine crystals over the moving crackers. The crackers pass beneath in tight rows. Each piece rollers pull leavening ingredients release gas. The laminated layers starts from pale dough to light gold. The final oven zone be tightly balanced. If the cracker leaves the oven too moist, it will soften in the package. If final texture. The crackers exit the oven extremely hot. They move directly toward the oil and salt application stage. Their heat helps the oil spread into a thin, even film. The salt attaches before the surface cools and stabilizes. After oiling and salting, the crackers enter a cooling conveyor. Air moves across the rows and draws heat away. The oil film settles. The cracker becomes fully crisp as its internal moisture evens out and the surface gathers them into vertical columns or short-counted stacks. The crackers slide against one another with their flat faces aligned. Stacking must be gentle. Ritz crackers are thin and crisp, so harsh impact would chip the scalloped edge. The machine controls the drop height and pressure around the stack. The film folds tightly enough to hold the crackers aligned, but not so tightly that it crushes the edges. Sour Patch Kids are made by cooking a concentrated sugar syrup, converting it into a soft, elastic gel, shaping that gel into small figures, drying the pieces to the right chew, then finishing them with sour crystals and a light oil coat so they stay separate in the bag. Production starts with ingredient preparation for the base syrup. Granulated sugar is stored in silos and screened so crystal size stays consistent. Glucose syrup or corn syrup is held in heated tanks so it pumps at a steady viscosity. Water is filtered and tempered because inlet temperature affects cook consistency, acid powders, and buffer. Salts are staged in microfeeders because sour candy needs tight pH control. Gel forming agents are prepared as separate streams because they hydrate differently and must be dispersed without clumps. Flavors and colors are staged in concentrated form, so dosing volumes remain small and precise. The first major operation is syrup cooking. Sugar and water enter a dissolver where agitation prevents settling and speeds dissolution. The clear sugar solution feeds a continuous cooker that drives off water and raises solids content. Heat is applied quickly to reach the target concentration without long residence time. Concentration matters because it sets final water activity and affects how the gel later firms. If the syrup is too wet, the candy stays sticky and dries slowly. If the syrup is too dry, the candy can set too hard and lose its soft bite. Glucose syrup is added during cooking to control crystallization. It limits uncontrolled graining that would make the candy sandy. It also changes viscosity and elasticity in the finished piece. Metering is done by flow control, so the ratio stays stable over long runs. The cooked syrup exits the hot zone and enters a flash or vacuum stage that stabilizes final solids. Vacuum finishing reduces thermal stress and helps protect flavor potential. Once the syrup hits target solids, it is cooled to a temperature that can accept sensitive ingredients. Cooling happens through heat exchangers that drop temperature in a controlled curve. At this point, acids are not added yet in many lines because high heat can drive inversion and can dull flavors. Instead, the syrup is cooled to a safer range where acids and colors can be introduced without degradation. Gel formation begins when the gelling system is incorporated. The exact system can vary by formula, but the process logic stays consistent. The gel agent must be fully hydrated and evenly dispersed before the syrup sets. Dry gel powders can clump on contact with hot syrup, so many. Lines prehydrate them as a slurry. The slurry is prepared in a separate tank with high agitation. The slurry then feeds into the main syrup stream through an injection manifold. Static mixers fold the streams repeatedly so there are no streaks. If starch is used as a texturizer, it is hydrated and cooked to develop viscosity. Cooking can occur in a separate cooker, and then the cooked starch stream is blended into the candy base. If gelatin is used, it is bloomed in water and then warmed until fully dissolved. The dissolved gelatin is then blended into the syrup under controlled shear. The objective is a uniform gel network that will set consistently in every cavity of the mold. Acid handling is central to Sour Patch Kids because the sour effect is staged. Part of the sourness can be in the candy body, and part is added later as a surface coating. For the candy body, acids are often added after the syrup is cooled enough to protect flavor and to avoid excessive inversion. The acid solution is metered into the stream and mixed thoroughly. pH is monitored because it affects gel strength and also affects flavor brightness. Too much acid can weaken certain gel systems and make the candy slump. Too little acid makes the interior taste flat and forces the surface coat to do all the work. Flavors are added late to preserve aromatics. Liquid flavors are injected through precision pumps into a turbulent zone. Oil-based flavors may be emulsified so they distribute evenly. Colors are added in parallel using metered pumps. Color must be consistent because small changes are visible on translucent gummies. The mixed candy base then moves toward depositing with minimal delay because gelation can begin as temperature drops. Shaping is typically done by depositing into starch molds or into rigid molds depending on line design. In starch molding, a tray is filled with dry starch and then imprinted with candy shapes. The imprinted cavities act as a mold and also act as a drying medium. The warm candy base is deposited into each cavity by a multi-nozzle depositor. Deposit weight is controlled because final piece size must be uniform for sour coating and packaging. The deposited gel begins setting as it cools in the tray. In rigid molding, the candy base is deposited into silicone or metal molds. The molds pass through cooling zones to set the gel. Rigid molding can produce sharper detail, but requires careful release control. Starch molding is common for gummy figures because it supports high volume and provides an integrated drying environment. After depositing, the pieces are held to set. Set time allows the gel network to develop enough strength for handling. Temperature and humidity in the setting area are controlled so the surface does not sweat. If the surface sweats, it picks up starch or dust and becomes rough. If the surface dries too fast, it can form a skin that traps moisture. Drying is the step that creates the final chew. Freshly set pieces still, hold more water than the finished candy. In starch, molding the pieces dry while sitting in the starch bed. The starch pulls moisture out gradually. Airflow across trays helps remove that moisture from the system. Drying time is tuned to reach a target moisture content and a target water activity. These targets control shelf stability and texture. Drying must be uniform through the batch. Uneven drying creates pieces that feel firm on the outside but soft inside. It can also create surface tack in some pieces. Tray stacking and airflow distribution are therefore designed to keep conditions consistent. Some lines move trays through conditioned rooms for many hours. Other lines use controlled tunnels with staged humidity to accelerate drying without case hardening. Once drying reaches target, the pieces are separated from the molding medium. In starch molding, the trays are dumped onto screens that break up starch and release candy. Vibrating sieves separate candy from starch. The starch is reclaimed and dried and sieved before reuse. Candy pieces are then brushed or air cleaned to remove residual starch dust. Clean surfaces matter because the next step is sour sanding, and dust can interfere with adhesion. At this stage, the candy has its base sweetness and its interior flavor. The defining Sour Patch Kids signature comes from the sour surface coat. Surface sour is applied as an acid sugar blend that adheres to the gummy exterior. This blend is made by mixing fine sugar with acids like citric and malic. Particle size is controlled so the blend clings evenly and dissolves at the intended speed in the mouth. Too fine a blend can cake and form uneven patches. Too coarse a blend can fall off during conveying. To make sour crystals stick, the gummy surface needs a controlled tack. The candy is not coated when it is wet because crystals would dissolve. It is also not coated when it is too dry because crystals would not bond. Many lines apply a very light mist of syrup or water to create temporary surface tack. The mist is extremely fine, so it does not melt the gummy surface. Immediately after misting, the candy enters a sanding drum, where the acid sugar blend is dosed. Sanding drums tumble the candy gently while sprinkling the sour blend. Tumbling distributes crystals across all surfaces. Drum speed is tuned so pieces roll and do not slide. Sliding can smear the tack layer and create streaks. The sour blend dose is controlled by mass flow, so every batch receives the same coating weight. Excess powder is screened off and recycled depending on quality control rules. Haribo Gold Bears are produced by cooking a concentrated sugar syrup, combining it with hydrated gelatin to create an elastic gel base, depositing that base into bear-shaped molds, drying the pieces to a defined chew, then finishing them with a light surface treatment so they remain separate and glossy in the package. Production begins with staging the main carbohydrate streams. Granulated. Sugar is stored in silos and screened to control crystal size and remove dust. Glucose syrup is held in jacketed tanks so it stays pumpable and meters accurately. Water is filtered and tempered because inlet temperature affects dissolving and cooking stability. Acidulants are staged in microfeeders because final pH influences flavor and gelatin performance. Flavors and colors are prepared as concentrated solutions so dosing volumes remain small and repeatable. Gelatin preparation is treated as its own process stream because gelatin must hydrate before it can dissolve. Dry gelatin is weighed and dispersed into cold water for blooming. Blooming allows granules to absorb water and swell. The bloomed gelatin is then warmed gently until it becomes a clear solution. Temperature is controlled to avoid damaging the gelatin network. The gelatin solution is held warm and mixed slowly to keep it uniform and free of undissolved lumps. In parallel, the sugar syrup is cooked to the correct solids, level. Sugar and water first enter a dissolver where agitation and heat create a clear solution. The solution feeds a continuous cooker that raises temperature rapidly and drives off water. Rapid cooking limits thermal damage and keeps color clean. Glucose syrup is injected at a controlled point to manage crystallization and viscosity. The ratio of sugar to glucose syrup defines how the final candy resists graining and how it chews. The cooked syrup exits the hottest zone and is often finished under vacuum. Vacuum finishing removes water at lower temperature, which reduces thermal stress. Solids content is brought to a target range that supports shelf stability and predictable drying. Solids that are too low produce gummy pieces that remain sticky and dry slowly. Solids that are too high can yield a firm glassy bite and reduced elasticity. After cooking, the syrup is cooled to a blending temperature that protects flavors and supports gelatin integration. Cooling is performed through heat exchangers that control the temperature curve. The syrup must still be warm enough to blend smoothly, yet cool enough that gelatin is not degraded. The cooled syrup enters a blending manifold where the gelatin solution is metered in. Combining syrup and gelatin is done with controlled shear. The system needs enough mixing energy to create a uniform gel base. It must avoid whipping air into the mixture because air causes bubbles and weak spots. Inline static mixers fold the flow repeatedly and create homogeneity without high-speed agitation. The blend becomes a hot, viscous liquid that will gel as it cools. Acid addition is timed carefully because acidity affects gelatin strength. Acids can weaken gelatin if added too early at high temperature. Many processors add acid after gelatin has been dispersed and after the blend has cooled further. Acid is often added as a solution for rapid dispersion. pH is monitored because a narrow range is needed for consistent flavor and texture. 2. High APH yields flat flavor and can alter set behavior. Too low APH can soften the gel and slow drying. Flavor and color are added late to preserve volatile compounds. Color solutions are metered into the flow and mixed thoroughly. Gold bears are produced in multiple colors and flavors, so the base may be split into parallel streams. Each stream receives its own flavor and color dosing. Dosing is controlled by mass flow and verified by concentration checks. Uniform color is important because translucent gummies show streaks easily. The finished hot candy base must be deposited quickly because viscosity rises as it cools. Depositing is typically done into starch molds. Starch molding starts by filling trays with dry starch and leveling the surface. A stamping board presses bear-shaped impressions into the starch. These cavities define the candy shape and also act as a moisture sink during drying. A multi-nozzle depositor moves over the trays and injects the hot candy base into each cavity. Deposit volume is controlled so each bear has consistent mass. The nozzle design and timing prevent stringing and tailing. The base fills the cavity and begins to set as heat transfers into the starch bed. The starch supports fine detail and prevents the pieces from spreading. After depositing the trays, move into a setting and drying environment. In the initial set stage, the gel network forms as the mixture cools. The surface becomes firm enough to hold the bear shape. This stage is managed so the surface does not skin too fast. A skin would trap moisture and slow drying. The starch bed helps regulate surface moisture by absorbing water gradually. Drying is the main step that develops the final Haribo-style chew. The deposited gummies contain more water than the finished product. Over time, water migrates from the gummy into the starch and then into the air. Drying conditions are controlled by room temperature and humidity and airflow. The process targets a defined water, activity, and a defined moisture content. These targets control bite resistance and shelf stability. Drying time is long enough to create a dense elastic chew rather than a soft gel. If drying is too short, the pieces stay soft and can stick. If drying is too long, the pieces become tough and can lose their characteristic bounce. Uniformity is essential so all pieces in a batch reach the same endpoint. Tray stacking patterns and airflow distribution are designed to avoid zones that dry faster than others. During drying, the gummy structure changes. The gelatin network becomes more concentrated as water leaves. Sugar concentration rises and the matrix becomes denser. The exterior becomes slightly firmer than the interior. This gradient contributes to the final bite. Managing the gradient is part of tuning the chew. Too steep a gradient creates a tough skin and a softer center. Too shallow a gradient yields a uniform softness that feels less elastic. Once drying reaches target, the pieces are separated from the starch. Trays are dumped onto vibrating screens that break the starch bed and release the bears. Screening separates bears from starch. Starch is reclaimed through a drying and sieving system so it can be reused. The bears pass through brushing and air cleaning to remove residual starch dust. Clean surfaces are needed for the finishing step and for appearance. At this stage, bears can be blended across flavors depending on the final pack. Blending must be gentle because partially dried gummies can still deform under heavy loads. Blend drums rotate slowly to mix colors evenly. The aim is consistent color ratio in each package and stable flow to the weighers. Surface finishing improves handling and visual shine. A light oiling step is common. A small amount of food-grade oil is misted in a finishing drum while the bears tumble. The oil forms a very thin film that reduces friction and prevents sticking. It also reduces dust by binding any remaining starch particles. Oil dosage is kept low because excess oil would feel greasy and could dull flavor. Some products use a glazing step instead of or in addition to oil. A glaze can be applied as a very thin film that dries to a shine. The film spreads as the bears tumble and it smooths micro texture. The finish helps pieces slide through packaging equipment and reduces scuffing. After finishing, the bears are screened again. Screening removes broken pieces and fines. Broken pieces are undesirable because they shed fragments and reduce visual quality. Metal detection is used before packaging to protect product integrity. Consistent size and smooth finish improve weigher accuracy and reduce jams. Packaging begins with feeding bears into multi-head weighers. Gummies must flow freely without bridging. Hoppers are designed with smooth walls and steep angles. Light vibration can be used to maintain flow. The weigher selects combinations of hopper dumps to reach the target weight. Accurate filling depends on stable piece weight and low clumping. Twizzlers are manufactured by building a cooked sweet base, converting it into a plastic dough with controlled elasticity, extruding that dough through shape dies into continuous ropes, setting texture through heat and moisture control, then cutting and packaging so the twists stay chewy and separate. Production starts with staging the main carbohydrate system because the finished chew depends on solids ratio and water activity. Granulated sugar is screened to control particle size and remove hard clumps. Corn syrup is stored in jacketed tanks so it stays pumpable at a stable viscosity. Water is filtered and tempered because inlet temperature influences dissolution and cook stability. Starches and proteins that contribute body are kept dry and free-flowing in sealed hoppers. Acids and salts are staged in microfeeders because small changes shift flavor intensity and dough behavior. Flavors and colors are prepared as concentrated solutions to keep dosing precise and repeatable. The first major transformation is syrup cooking and solids control. Sugar and water enter a dissolver where agitation prevents settling and speeds dissolution. The clear solution feeds a continuous cooker or batch kettle where heat drives off water and raises solids. Corn syrup is metered into the stream to control crystallization and to keep the base pliable. Temperature and residence time are controlled tightly because undercooked syrup leaves excess water and makes the final product sticky. Overcooked syrup becomes too viscous and makes later mixing difficult. As the syrup reaches target concentration, it is cooled to protect sensitive ingredients and to prepare for the next mixing stage. Cooling is done with heat exchangers that drop temperature along a controlled curve. The syrup must stay warm enough to flow through pumps and static mixers. It must cool enough to avoid damaging flavors and to avoid unwanted browning. The cooled syrup enters a blending manifold where functional solids can be introduced. Building the Twizzlers style matrix relies on combining syrup with dry structure forming ingredients. A common approach uses starches or similar polysaccharides to create chew and to reduce tack. These dry ingredients must be dispersed without forming lumps. They are fed through loss in weight feeders into a high shear mixer or twin screw mixer. The hot syrup wets the powders and begins hydration. Shear breaks down agglomerates and creates a uniform paste. The paste transitions from glossy syrup to a thicker plastic mass as solids hydrate and bind water. Hydration control is critical in this stage. If hydration is incomplete, the dough will contain dry pockets that tear during extrusion. If hydration is excessive, the mass can become too soft and lose definition after forming. Temperature helps control this because higher heat speeds hydration and reduces viscosity. Lower heat preserves shape but increases mixing load. The process targets a defined dough temperature that supports both mixing and extrusion. Acid and salt additions are timed to avoid destabilizing the structure. Acids are often added after the main hydration begins because early acid can change viscosity and affect hydration rate. The acid is typically added as a solution for faster dispersion. Flavors are added late because many are volatile and can be stripped by heat and shear. Colors are added in controlled doses and mixed until uniform because streaks are visible in translucent candy. Mixing continues until the mass is homogeneous in color and consistent in torque. Once the base dough is formed, it enters a conditioning stage that equalizes temperature and moisture. Conditioning can occur in a holding hopper with gentle agitation. It can also occur within a screw conveyor that provides controlled residence time. The goal is to let water distribute evenly through the mass. Even distribution reduces pressure spikes at the extruder and improves surface smoothness. Extrusion is the defining shaping step for Twizzlers. The conditioned dough is fed into an extruder that compresses it and pushes it through a die. The extruder can be single screw or twin screw depending on throughput and mixing needs. The barrel is temperature controlled so the dough stays plastic and stable. The screw geometry controls compression and shear. Compression removes trapped air and densifies the dough. Controlled shear aligns the matrix so the rope exits with smooth surfaces. The die determines the rope profile. For rope-style candy, the die can be round. For pull-apart styles, the die can form multiple channels that are later separated. Die temperature is managed because cold dies can cause surface cracking. Hot dies can cause surface smear and sticking. Pressure at the die is monitored because it reflects dough viscosity and feed consistency. Stable pressure yields stable rope diameter. As the rope exits the die, it is still warm and flexible. It must be guided and shaped before it sets. A calibration section can include sizing rollers or a vacuum sizing tube that stabilizes diameter. The rope is supported by belts that carry it forward without stretching. Stretch changes thickness and also changes texture because it aligns the structure too strongly. Belt speed is synchronized with extruder output to maintain constant rope tension. Twist formation is done by controlling motion and differential speed. One method uses paired belts that rotate the rope as it moves forward. Another method uses spinning heads that grip the rope and impart twist while a takeoff belt pulls. The twist rate is controlled by the speed difference between the rotating element and the takeoff belt. A tighter twist creates a denser appearance and a firmer bite. A looser twist yields a smoother rope with less surface definition. The twist must remain consistent along the entire length to avoid weak spots and uneven chew. After twisting, the rope enters a setting and drying pathway. Setting stabilizes the shape and fixes the surface so it does not unwind. Drying adjusts moisture to reach the final chew and to prevent sticking in packaging. The process uses controlled air tunnels where temperature and humidity are tuned. Warm air drives off moisture and firms the surface. Air must not be so hot that it causes case hardening. Case hardening creates a tough skin with a softer core. That texture feels uneven and can cause splitting during bending. Drying is managed as staged zones. Early zones remove surface moisture and lock the twist ridges. Mid zones remove moisture more gently to preserve uniformity through the cross-section. Later zones bring the rope to a stable moisture endpoint. The endpoint is defined by water activity and by texture tests. If moisture remains too high, the candy sticks and deforms. If moisture is too low, the candy becomes hard and can crack when twisted or bitten. Cooling follows. Drying, because the rope must reach a stable temperature for cutting and handling. Cooling also allows internal moisture gradients to equalize. As the rope cools, the matrix becomes more resilient and less tacky. Cooling air is often controlled for humidity because dry air can overdry surfaces and change bite. Humid air can soften surfaces and increase sticking. The process targets stable conditions that preserve the intended chew. If the product requires a glossy surface, a finishing step can be applied. A light oil mist can reduce friction and improve flow through cutters. The oil film must be minimal because heavy oil would create greasy mouthfeel and would attract dust. Some lines apply a thin glaze rather than oil. A glaze can improve shine and reduce stick. The glaze must dry or set before cutting to avoid smearing. Cutting converts the continuous rope into consumer lengths. A rotary knife or guillotine cutter slices the rope at a fixed pitch, synchronized to belt speed. Cut. Length defines piece weight and pack count. Knife design matters because a dull blade can drag and deform the twist ends. A clean cut preserves the twist profile and reduces strings. Cutting stations often include vacuum or air assistance to clear fragments and keep the area clean. After cutting, the pieces are separated and oriented for packaging. Separation prevents pieces from nesting and sticking together. Conveyors use gentle transitions because candy can deform under impact when warm. The process aims to keep pieces within a defined temperature range. Too warm and they flatten at contact points. Too cool and they become stiff and can chip at the ends. Nerds begin as a hot, clear sugar melt that is deliberately forced into a brittle glass because the final candy is defined by controlled fracture rather than molding. The line starts by preparing a sugar solution that can be concentrated without seeding unwanted crystals. Granulated sugar is screened to remove clumps and to tighten the crystal size range. Fines are limited because they dissolve too fast and can caramelize at hot surfaces. Water is filtered and tempered so dissolution conditions stay repeatable. Corn syrup is held in jacketed tanks to keep viscosity stable for metering. Acid powders, salts, flavors, and colors are staged in. Separate feeders because nerds often run multiple flavors in parallel. Sugar and water enter a dissolver with strong agitation. The goal is a fully dissolved solution with no grain residue. Any undissolved grain becomes a nucleation site that can trigger premature crystallization. The solution passes through strainers to remove stray solids and then feeds a continuous cooker. In the cooker, the syrup is heated rapidly to drive off water and raise solids to the level needed for a hard candy glass. Many systems heat under pressure so temperature can rise above the normal boiling point without flashing. That allows fast heat transfer and short residence time. The syrup then enters a flash stage where pressure drops and water vapor leaves quickly. Flashing tightens final moisture and also cools the syrup slightly by evaporative loss. Final solids must land in a narrow window. Too wet and the sheet will bend and tear instead of shattering. Too dry and the sheet will explode into excessive dust when fractured. Corn syrup is injected as a crystallization control lever. It reduces uncontrolled graining and helps keep the candy glass consistent from run to run. Its metering is precise because it also changes brittleness and fracture behavior. After the final concentration step, the syrup is cooled through heat exchangers to a temperature that protects flavors and supports controlled casting viscosity. The process often splits into two streams at this stage to create two flavors and two colors for the paired pack format. Each stream receives its own acid and flavor additions. Acid is added after the hottest zones because high temperature and low pH accelerate sucrose inversion and can change texture. The acid is usually dosed as a solution to ensure fast dispersion. pH is controlled because it influences sourness and also influences how hygroscopic the finished candy will be. Flavors are injected late and mixed rapidly. Oil-based flavors are emulsified or carried so they will disperse evenly. Color solutions are filtered and then metered into each stream. Uniform color matters because nerds are small and translucent and any streaking is visible. Static mixers fold the flow repeatedly to eliminate bands before casting. Casting turns the hot syrup into a thin sheet that can be fractured into granules. The syrup is deposited onto a cooled steel belt or onto trays as a continuous ribbon. Deposit rate and belt speed set thickness. Thickness is a key variable because it determines cooling rate and fracture size distribution. A thicker sheet cools slower and can retain internal stress. A thinner sheet cools fast and can become too brittle at the surface. Cooling is engineered to produce an amorphous glass with minimal crystal growth. Cooling plates under the belt pull heat out evenly. Air above the sheet is controlled so humidity does not condense, and so surface remains clean. Rapid cooling locks the syrup into a glassy state. If cooling is too slow, crystals can grow and the candy becomes gritty rather than sharp and crunchy. As the sheet cools, it can be conditioned to create predictable fracture behavior. Some lines flex the sheet slightly over rollers to introduce controlled microstresses. Others lightly score the surface to create preferred break paths. The aim is to reduce random oversized chunks and reduce the need for aggressive crushing later. The sheet must reach a brittleness that breaks cleanly under compression rather than smearing. Once the sheet is brittle, it is released from the belt and fed into a primary breaker. The primary breaker uses toothed rollers or oscillating bars to crack the sheet into chips. This first break is staged to avoid shattering into dust. Chips then feed a secondary reduction stage, often roll crushers, that bring pieces down toward the final nerd size range. Roll crushers are used because they apply compressive force and yield angular fragments rather than rounded beads. Crusher gap is the main size control. A smaller gap yields more fines and a narrower top size. A larger gap yields more oversize that must be recirculated. Feed rate must be steady because surges cause inconsistent reduction and more dust. Roll speed and surface texture also matter because they control how the chip is gripped and fractured. The goal is irregular pieces with sharp facets but limited powder. After crushing the material enters screening. Vibratory screen decks separate by size in multiple fractions. The target fraction continues as product. Oversize is returned to the crusher for another pass. Fines are removed because they clump easily and create dusty packs. Fines can be used as controlled recycle seed in some systems, but only in small ratios because they raise cohesion and reduce free flow. Because nerds often come in two distinct colors, each stream is processed separately through crushing and screening. This keeps recycle loops color pure and prevents shade drift. It also allows each stream to be tuned for its own brittleness because acid and flavor loads can shift glass strength. If one flavor tends to shatter more, the crusher gap can be opened slightly for that stream while keeping the other tighter. Conditioning follows sizing. Even though the candy is glassy, it can hold slight moisture gradients from casting and cooling. Conditioning allows moisture to equalize inside each granule. This stabilizes crunch and reduces caking risk. Conditioning bins use controlled dry air so the product does not absorb humidity. Humidity control is critical because hard candy surfaces can become tacky when water activity rises. Tack leads to clumping and also to color transfer between pieces. A light finishing step can be applied to improve flow. Anti-caking agents can be dusted at very low levels in a tumbler. The purpose is to reduce surface adhesion points and to improve hopper flow. Application must be uniform because local over-application changes mouthfeel and creates visible dust. After tumbling, the product can be aspirated lightly to remove excess loose powder. For versions that emphasize a stronger sour burst, some sourness can be placed at the surface rather than only in the body. This is done by misting a very small amount of binder and then applying an acid-sugar blend. The binder must be extremely light so it does not dissolve the glass surface. The acid blend adheres, and then the product is dried quickly to set. This creates a fast sour hit at the tongue because surface acids dissolve first. If the product format requires blending the two flavors, blending is performed after each stream has been sized and conditioned. Gravimetric feeders meter each color stream into a blender at the target ratio. The blender uses gentle paddles, so it mixes without grinding. Over-mixing would generate fines by abrasion. The blending time is therefore short, and the geometry is chosen to fold the streams rather than shear them. Before packaging, the blended product is screened again to remove any fragments created in blending and conveying. This final screen improves pack cleanliness and improves weigher accuracy. Metal detection can be placed at this stage because product flow is stable and pieces are dry. Packaging begins with controlled feeding into weighers. Multi-head weighers are common because they can combine multiple small hopper dumps to reach target weight quickly. Consistent flow into the weigher depends on low fines and low humidity. Hopper walls are steep and surfaces are low friction. Vibration is used sparingly because vibration can create abrasion dust. For bag formats, the weighed portion drops into a vertical form fill-seal machine. Film is formed into a tube and sealed longitudinally. The portion drops through a funnel and settles. Transverse seals close the bag above and below the portion. Seal timing must keep granules away from the seal jaws. Dust management is important because sugar dust in the seal area can weaken the seal. Oreos are manufactured by producing a cocoa cookie wafer with a controlled snap and surface texture, producing a fat-based creme that holds shape without refrigeration, then assembling two wafers around a measured cream deposit before packaging to protect crispness. The cookie wafer begins with flour and cocoa handling because particle size and moisture define dough behavior. Flour is sieved to remove lumps and to aerate it for consistent hydration. Cocoa powder is sifted because it compacts and forms clods that create dark streaks. Sugar is screened to control crystal size and reduce dust. Leavening and salt are weighed precisely because they drive spread and porosity. Fats are tempered to a plastic consistency so they cream evenly and do not separate during mixing. Water is tempered because dough temperature controls sheeting and bake spread. Mixing starts by building a fat-sugar phase that controls texture. Fat and sugar enter a mixer and are creamed until sugar crystals are uniformly wetted and small air cells are incorporated. Air incorporation is controlled because it influences wafer porosity and snap. Too much air yields fragile wafers that crumble during sandwiching. Too little air yields dense wafers that lack the intended crisp bite. Salt and leavening can be added during creaming so they disperse evenly through the fat phase. Water is introduced next in a controlled stream. The water level is set to produce a dough that sheets cleanly without sticking. Water also activates leavening and hydrates flour. Cocoa powder and flour enter after water, so they are hydrated evenly. Mixing energy is reduced during flour addition to limit gluten development. Excess gluten makes wafers tough and increases shrink during baking. The end point is a cohesive dough that is uniform in color with no dry pockets. The dough is then conditioned for forming. Conditioning allows moisture to distribute and lets the dough relax so it does not snap back after sheeting. Dough temperature is held in a narrow band. Warm dough becomes sticky and smears on rollers. Cold dough cracks and produces rough edges. The line uses controlled dwell time and jacketed hoppers to maintain stable dough temperature. Sheeting converts dough into a continuous band at a defined thickness. The dough passes through a series of reduction rollers that gradually thin it. Multiple reduction stages prevent tearing and keep texture uniform. Gauge rollers set the final thickness tightly because thickness controls bake time and final snap. Surface flour dusting can be used sparingly to prevent sticking. Excess dusting is avoided because it burns and creates specks. The sheet enters rotary cutting and embossing. Rotary cutters punch round wafers from the sheet while an embossed pattern is pressed into the surface. The embossing is functional. It controls thickness uniformity, adds texture, and influences how creme bonds. Docking holes are also created during this step. Docking vents steam during baking and prevents blistering. The sheet scrap around the cutouts is lifted and recycled back into the dough stream under controlled ratios. Scrap ratio is limited because repeated working increases gluten and changes dough rheology. Cut wafers transfer to an oven band and enter a tunnel oven. Baking is zoned to set structure and drive moisture to a low endpoint. Early zones melt fat and allow the dough to expand slightly as leavening gases form. Starch gelatinizes and protein set, turning the dough into a porous solid. Mid-zones develop color and drive off moisture. Later zones finish drying so the wafer becomes crisp and stable. Moisture endpoint is critical. If moisture is too high, wafers soften in the package and the sandwich loses snap. If moisture is too low, wafers become brittle and crack during assembly. Oven temperature and airflow are tuned to reach a narrow moisture band. Airflow affects surface drying and color. Strong airflow dries faster and can increase snap. Lower airflow yields a gentler bake and can retain a softer bite. The line controls top and bottom heat to prevent warping and ensure even bake across the wafer. After baking, wafers exit hot and fragile. Cooling stabilizes structure as fats resolidify and moisture equilibrates. Cooling conveyors use controlled airflow. Dehumidified air is often used because crisp wafers can absorb moisture from humid air. Cooling brings wafers to a temperature suitable for creme application. Wafers that are too warm will soften the creme on contact and can cause slip. Wafers that are too cool can be brittle and prone to edge chips. Wafers are sorted and oriented for assembly. Vision systems can reject misshapen wafers and cracked wafers. Thickness checks and color checks verify the oven profile. Good wafers are aligned in lanes, so the embossed side faces the correct direction. Alignment is important because the pattern must be consistent on the outside of the sandwich. Cream. Manufacture runs as a separate stream because it is a fat-based system that must remain stable and non-gritty. The cream is built from sugar, fat, and emulsifiers plus flavor. Sugar is milled or selected to a fine particle size so the cream feels smooth. The fat base is prepared from vegetable fats that are melted and then cooled to a specific plastic state. Plastic state matters because it determines how the cream whips and how it holds shape. Cream mixing begins by blending fat and fine sugar under shear. The mixture transitions from dry and crumbly to smooth as fat coats sugar particles. Emulsifiers are added to reduce viscosity and improve spread. Flavor is added late so it remains strong. The cream is mixed until particle wetting is complete and the texture is uniform. Air can be incorporated in a controlled way to adjust density. Higher aeration yields a lighter cream that compresses easily. Lower aeration yields a denser cream with firmer bite. Temperature control in the creme is critical. If the creme is too warm, it becomes too fluid and can squeeze out during sandwiching. If it is too cold, it becomes stiff and can crack or fail to adhere. The process holds creme in a narrow temperature range where it is depositable and retains sharp edges after deposition. Cream is delivered to the assembly line through heated or conditioned piping. The depositor meters a precise mass onto each wafer. Depositing is typically done as a spiral or star pattern. The pattern controls spread when the top wafer is applied. The deposit height determines final sandwich thickness. Weight control is tight because it affects bite and package count weight. As soon as cream is deposited, a second wafer is placed on top. Placement systems pick wafers and align them over the cream deposit. The wafers are pressed together with a controlled compression. Compression spreads the cream to the edge without breaking the wafer. Too much compression crushes wafers and causes overspread. Too little compression leaves a tall deposit and weak adhesion. Compression also sets the final wafer to creme contact, which controls stability during transport. After sandwiching, the cookies move through a short setting conveyor. During this stage, the creme fat network stabilizes and holds the sandwich geometry. Cooling can be applied to firm the cream slightly. The goal is a sandwich that can be handled and packed without creme smear. The product is then inspected. Vision checks can detect misaligned wafers and missing cream. Rejects are removed automatically. Packaging is designed to protect wafers from humidity and to protect sandwiches from breakage. Sandwich cookies are stacked into columns and placed into trays. Trays hold stacks in position and reduce movement that would chip edges. The tray is then sealed inside a moisture barrier film. Film barrier performance is critical because wafer crispness depends on low moisture pickup over time. Stacking is controlled, so columns are uniform height. Uniform columns prevent uneven pressure that can break wafers. The stacking system uses lanes and pushes that align cookies without scuffing. Crumb control is important because crumbs in seal areas can compromise seal integrity. The line uses crumb extraction near tray loading and near sealing stations. The tray and film system passes through a heat seal station where the film is sealed to the tray. Seal temperature and dwell are tuned to create a continuous seal without warping the tray. Leaks allow moisture ingress, which softens wafers. Sealed trays are coded and checked by vision. Check weighers confirm pack weight. Sealed trays are then inserted into outer cartons. Cartons are erected and loaded with trays. Cartons add stacking strength and protect the film from puncture. Cartons are closed and glued. Finished cartons are case-packed and palletized. Snickers starts as 3 independent streams that only meet at the assembly belt because nougat, caramel, and chocolate each require different heat histories and different flow behavior to stay consistent at scale. The nougat stream is built around controlled aeration. Sugar and glucose syrup are metered into a cooker and concentrated to a target solids level that will support a stable foam once mixed. The cook profile is kept short because long high heat residence darkens sugars and shifts viscosity. The syrup exits the hottest zone and is conditioned to a temperature where it can strengthen a protein foam without scorching it. In parallel, a foaming phase is prepared as a protein solution that can hold fine bubbles. The solution enters a continuous aerator where airflow and shear are controlled to generate a narrow, bubble-sized distribution. Density is measured continuously because density drives bar weight and final bite. If density drifts, the bar becomes heavy and tight. If density drops too far, the nougat becomes fragile and can collapse during cutting. The hot syrup and the foam meet in a continuous mixer designed to fold rather than whip. Folding distributes syrup through the foam while preserving bubble walls. The syrup heat partially sets the protein films and locks the microcell structure. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be dosed in small amounts to stabilize the air-fat sugar system and to keep the nougat smooth as it cools. Once the nougat reaches specification, it is deposited as a continuous slab onto a moving belt. A spreader head lays down a uniform band, and gauge rollers set thickness. Thickness control matters because it defines the core cross-section and the later chocolate ratio. The slab enters a cooling tunnel with staged zones that remove heat gradually. Gradual cooling prevents a hard surface skin forming over a warm interior because that skin can crack when the slab is bent or cut. While nougat is being formed, a caramel stream is cooked in parallel. Caramel starts as sugar and glucose, syrup combined with dairy components. The cook concentrates the mix to a solids endpoint that yields elasticity rather than glassiness. If solids are too low, the caramel flows and smears on knives. If solids are too high, the caramel fractures and creates sharp cracks under the chocolate coat. Fat is added near the end to smooth texture and reduce tack. The caramel is then cooled to a working temperature where it remains depositable and stable. Caramel is held in jacketed tanks with gentle agitation to prevent a surface skin. It is delivered to a depositor through heated lines that keep viscosity constant. The depositor is designed to lay down an even sheet rather than a rope. An even sheet is important because Snickers requires predictable bite across the full width of the bar. Peanuts are handled as their own stream because their size and dryness control both crunch and line stability. Roasted peanuts are screened to remove fines and broken fragments that would create dust and weak points. The nut size band is chosen to give a consistent surface coverage without tall peaks. Peaks can pierce the chocolate curtain and create thin spots. Peanuts are cooled after roasting, so residual heat does not soften caramel and does not melt chocolate during enrobing. Assembly begins when the cooled nougat slab reaches the layering station. Caramel is deposited onto the nougat as a continuous layer with a controlled thickness. A leveling bar spreads the caramel and smooths the surface. The temperature of both layers is managed closely. The nougat surface must be firm enough to support caramel without compression. The caramel must be warm enough to bond without sinking into the nougat. Immediately after caramel deposition, peanuts are applied. A spreader distributes nuts across the width with a calibrated feed rate. The nuts land on caramel while it is still tacky, so they adhere. A light compression stage can press nuts into the caramel to improve lock-in. Compression is tuned, so it increases contact without crushing nuts into fragments. The layered slab then enters a conditioning zone. This zone firms the caramel enough for clean cutting and locks nut position. Conditioning is staged to avoid large thermal gradients between nougat and caramel. Large gradients cause differential contraction and can create separation lines. The goal is a slab that behaves as one piece under knives. edge trimming follows because slab edges often vary in thickness. Rotary knives remove edges and send trim to controlled rework streams. The main slab is then cut into lanes. Lane knives create long ropes of constant width. A crosscutter then cuts the lanes into bar lengths. Knife timing is synchronized with belt speed to maintain tight weight control. Knife surfaces and temperatures are managed because caramel can stick and smear if the blade is too warm or too cold. The cut bars are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges between adjacent bars. Transfer points minimize drop height because impact can dislodge nuts and can dent the nougat. A brief pre-chill can be used to firm the bar surfaces. Firmer surfaces improve chocolate coverage and reduce nut movement during curtain contact. Chocolate coating is prepared in a separate system where temper is the critical parameter. Chocolate is melted and filtered to remove unmelted particles. It is tempered in a continuous tempering unit that heats and cools in stages. The process builds stable seed crystals and then sets a working temperature that keeps viscosity steady. Viscosity matters because it defines curtain thickness and therefore coating weight. If viscosity drifts, the bars become heavy or exposed. Enrobing applies chocolate with a top curtain and a bottoming system. Bars pass through a chocolate waterfall that coats the top and sides. The underside is coated by a bottoming roller or a bath section that lays a uniform base. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the thickness at edges and the foot at the base. Air knife settings are tuned so they remove excess without exposing nuts at corners. If a top pattern is used, a stringer drizzles thin lines across the wet surface. The pattern must be applied while the base coat is still tacky enough to bond. The bars then enter the cooling tunnel immediately, so the coat sets without slumping. Cooling is staged to protect chocolate crystal structure and to prevent cracks around nut peaks. The first zone sets the surface quickly, so the coat holds shape and locks nuts in place. Subsequent zones cool more gradually, so stable crystals grow without stress. Tunnel humidity is controlled to prevent condensation because condensation can create bloom and surface haze. Bars exit at a temperature that supports wrapping without scuffing. During cooling, the internal layers also stabilize. Nougat firms as its fat phase crystallizes and its bubble. Walls become more rigid. Caramel reaches its final elasticity and stops flowing at the interface. The chocolate coat becomes a barrier that slows moisture exchange and protects texture. Inspection follows cooling because surface defects are easier to detect when the coat is fully set. Vision systems check for exposed edges and bald spots and heavy feet. Weight checks verify that cutter control and coating control are stable. Metal detection can be placed before wrapping. Defective bars are diverted to rework. Rework is managed carefully because tempered chocolate cannot be recycled directly into tempered streams without remelting and retempering. Wrapping begins with steady bar spacing into a flow wrapper. Film is formed around each bar and sealed with heat and pressure. Sealed well and temperature are tuned to create strong seals without shrinking film onto the chocolate. Film tension is controlled to prevent scuffing. Code printing is applied for traceability. Wrapped bars can be collated into multi-packs or cartons. Collation uses lanes and gating, so bars group without impact. Cartons are erected and loaded and closed. Finished units are case-packed and palletized. Case patterns reduce movement that can abrade wrappers and stress seals. The Reese's Peanut Butter Cups process starts with peanut handling because peanut chemistry drives filling texture and oil stability. Roasted peanuts are cleaned with screens and air separation to remove shells and fines. The roast endpoint is controlled to set aroma and to reduce moisture so the paste is stable. After roasting, the peanuts are cooled quickly so residual heat does not thin the paste and does not accelerate oil separation. Grinding converts roasted peanuts into peanut butter. Nuts pass through staged grinders that reduce particle size while releasing oil to create a continuous fat phase. Temperature rises due to friction, so jackets and controlled throughput keep the paste within a narrow range. The paste is refined until it is smooth enough for the target mouthfeel. If particle size is too coarse, the filling feels gritty. If too fine, the filling can become overly dense and lose the characteristic crumbly bite. Filling formulation then turns peanut paste into a depositable mass that sets cleanly. Powdered sugar is sieved to remove clumps and to ensure a consistent fine size. Milk powders, cocoa powders, and salt are staged as dry micro-ingredients. A fat stream such as cocoa butter or another compatible fat can be used to tune firmness and melt. Emulsifiers can be added to stabilize oil distribution and improve flow through depositors. Mixing begins by combining peanut paste with dry ingredients in a high-torque mixer. Dry powders are added gradually so they wet without forming islands. The mixture transitions from glossy paste to a thicker, crumbly mass as sugar and powders absorb free oil. Mixing energy is tuned because it determines final texture. Overmixing can create a smooth paste that loses the signature short bite. Undermixing leaves dry pockets that cause weak structure and dosing errors. The filling is then conditioned for deposit. Conditioning equalizes temperature and allows fat crystals to form in a controlled way. If the filling is too warm, it flows and smears under the chocolate cap. If too cool, it becomes stiff and will not level in the cup. The line targets a narrow temperature band that supports clean deposits with sharp edges. The filling can be held in jacketed hoppers with gentle agitation, so it stays uniform without being whipped full of air. Chocolate preparation runs as a separate stream because shell quality depends on temper. Chocolate is melted in jacketed tanks and filtered to remove unmelted particles. It is then tempered through a staged heat and cool cycle that builds stable cocoa butter seed crystals. Working. Temperature is held tightly because viscosity determines shell thickness and because temper drift causes bloom and weak snap. Paper liners are fed to the forming line as a continuous stream. A denister separates liners and places them into cavities on a moving mold plate. The mold plate supports the liner so it holds shape during chocolate dosing. Liner position is controlled because misalignment causes thin spots and uneven rims. Forming the chocolate cup begins with depositing tempered chocolate into each lined cavity. Deposit volume is controlled because it sets shell thickness and final weight. After deposit, the molds are vibrated or spun to drive chocolate up the liner walls and create a thin, even shell. Spinning forces chocolate outward and leaves a hollow center. Vibration removes trapped air and smooths the surface. Spin speed and time control wall thickness. Too much spin makes walls too thin and fragile. Too little spin leaves heavy shells and reduces filling capacity. After shell formation, the cups enter a short cooling stage. Cooling sets the chocolate enough that the shell holds shape for filling. Cooling is staged so the shell contracts slightly without cracking. The shell must remain receptive at the interior surface so the filling bonds. If the shell is too cold, it becomes slick and can cause delamination at bite. If too warm, it deforms during filling and can smear. Filling deposition follows. The filling is dosed into each shell as a measured puck or mound. Deposit weight is tightly controlled because it defines bite and also determines whether the cap will seal cleanly. The filling can be deposited as a single shot or as a spiral. A spiral can improve leveling and reduce trapped air. The filling surface is controlled so it sits below the rim and leaves space for the chocolate top. A light leveling step can be used to control filling height. Leveling can be done by vibration or by a smoothing tool. The objective is a consistent fill height across all cups so the top chocolate spreads evenly. Leveling must be gentle because aggressive vibration can smear filling onto the rim, which contaminates the cap seal. Top chocolate application seals the cup. Tempered chocolate is deposited over the filling. The deposit must spread to meet the shell rim and create a continuous seal. Deposit volume determines top thickness. Too thin a top can crack and expose filling. Too thick a top can dominate bite and slow cooling. Some lines use a slight vibration after topping to level the surface and release bubbles. This vibration is controlled so it does not cause chocolate to climb over the liner edge. The filled and capped cups then enter the main cooling tunnel. Cooling is staged to promote stable cocoa butter crystallization and prevent bloom. Early cooling sets the surface quickly so the top does not slump. Later, cooling removes heat gradually so the entire chocolate mass crystallizes uniformly. If cooling is too fast, internal stress can create fine cracks around the rim. If too slow, throughput drops and cups can scuff in handling. During cooling, the peanut filling also stabilizes. Fat in the filling crystallizes and locks the short, crumbly texture. Moisture migration is minimal because both phases are fat continuous. The main interface risk is oil migration that can soften chocolate if the barrier is weak. Stable temper and proper cooling reduce this risk by creating a tight crystal network in the chocolate. After cooling, the cups are demolded. The mold plate releases the lined cups and they transfer to conveyors. Handling is gentle because the rim can chip. Vision inspection can check top coverage and detect deformed liners. Weight checks confirm dosing stability. Metal detection can be placed before wrapping. Wrapping depends on format. Individually wrapped cups are fed into a flow wrapper that forms film around each cup and seals it. Seal temperature and dwell are tuned so the film closes without melting the chocolate surface. Film tension is controlled so it does not crush the cup. For multi-packs, cups are collated into groups and then overwrapped or cartoned. Trays can be used to prevent movement and rim damage. After primary packaging, packs are coded and checked. Check weighers confirm net weight. Vision systems verify seals and codes. Finished units are case packed and palletized. Storage temperature stability is important because warm conditions soften the filling and stress the chocolate temper. Stable storage preserves snap and prevents bloom. The critical controls in Reese's cup production are peanut paste consistency, filling temperature and texture, chocolate temper, shell thickness, and cooling profile. Peanut paste consistency and dry ingredient ratio determine filling firmness and short bite. Filling temperature determines whether deposits are clean and whether oil separates. Chocolate temper determines gloss and snap and bloom resistance. Shell thickness determines structural strength and the chocolate to filling ratio. Cooling profile determines crystal stability and demolding reliability. Ferrero Rocher is built by synchronizing 4 separate manufacturing tracks that converge only at the assembly belt: roasted hazelnuts, wafer shells, hazelnut cocoa cream, and tempered chocolate for coating and adhesion. Hazelnut preparation starts by turning raw kernels into 2 distinct inputs. One stream becomes whole center nuts, and the other becomes chopped outer pieces and paste for the filling. Incoming hazelnuts are cleaned with screens and air separation, so stones, dust, and shell fragments are removed before roasting. The nuts are then graded by diameter. Tight grading matters because the center nut must fit the wafer cavity without stressing the shell or shifting the final mass balance. Roasting develops aroma and sets crunch by driving down moisture. Nuts travel through a roaster with a controlled temperature curve, so heating is even from surface to core. Roast endpoint is chosen to create a crisp bite without scorching oils. Immediately after roasting, the nuts are cooled in high airflow beds, so residual heat does not continue cooking, and so the nuts do not warm the cream during later insertion. Skin removal follows because loose skins create bitter flecks and interfere with adhesion in the outer nut coat. Nuts pass through rubbing rollers that loosen skins, then aspiration pulls skins away from the heavier kernels. Whole nuts are separated from broken pieces. Whole nuts go to the center insertion system, and broken pieces go to chopping and paste lines. Chopped hazelnuts for the exterior require a narrow particle size band. Roasted kernels are cut with calibrated knives or granulators and then screened. Oversized pieces are returned for further reduction, and fines are removed because fines behave like dust and reduce visual definition. The chopped nut bed is held dry and free-flowing so it can coat evenly when the chocolate is still tacky. In parallel, a portion of roasted nuts is milled into paste. Milling is staged so particle size drops gradually, while temperature is controlled to prevent oil separation. The paste is refined until it is smooth enough for a cream with no gritty perception. Wafer manufacturing runs independently because wafer is a dry, brittle structure that must stay crisp through later contact with fats. Wafer batter is mixed from flour, sugar, water, and small fat additions to reach a thin, pourable viscosity. Mixing aims for uniform hydration rather than gluten development because gluten would make wafers leathery. The batter is filtered to remove lumps that would create thin holes in the baked sheet. Baking takes place on heated wafer plates that cook the batter into very thin, porous sheets by rapid water evaporation. The bake profile targets low final moisture, so the sheet becomes rigid and crisp without scorching. Forming converts wafer into shells with consistent thickness and rims. One approach presses warm wafer sheets into hemispherical cavities, while the wafer still has slight pliability. The pressed halves are trimmed to clean rims because rim quality determines seam strength. Another approach uses shaped baking plates that form shells directly, then trims edges to uniform height. Either way, cracked halves are removed because small cracks become leak paths for cream and also become weak points during coating. The good halves move to a joining station where two halves are aligned. Shell joining creates a hollow sphere that must survive filling and coating. A thin ring of adhesive is applied to the rim. The adhesive is typically a fat-based compound or chocolate-based film that bonds quickly without wetting the wafer. The two halves are pressed together with controlled force so the seam closes without crushing the wafer wall. The joined spheres pass through a short cooling zone so the seam sets and the shells become rigid enough for filling. The hazelnut cocoa cream is produced as a fat continuous paste that must be smooth, stable, and pumpable. Hazelnut paste is blended with sugar, milk solids, and cocoa components. Refining reduces the particle size of sugar and solids so the cream feels smooth rather than sandy. The mass is mixed under controlled heat to distribute fats and to reduce moisture that would thicken the cream unpredictably. The final viscosity is tuned so it can be dosed precisely into wafers without trapping air pockets. The cream is held in jacketed tanks with gentle agitation so it remains homogeneous and does not develop surface skin. Chocolate for coating is prepared and tempered as its own process because stable crystals control set speed and surface quality. Chocolate is melted, filtered, and then tempered in stages to create stable seed crystals. Working temperature is set so viscosity remains steady at the curtain and so the chocolate stays tacky long enough to accept chopped nuts before setting. Assembly begins at the filling belt, where wafer spheres are indexed and presented to deposit heads. The first cream dose is applied to create an inner bed. This dose must coat enough of the interior to support the nut and to reduce rattle. The nut insertion system singulates whole nuts so they feed one at a time. Each nut is centered and placed into the cream bed with controlled depth. Depth is important because it determines how much cream surrounds the nut and whether the sphere remains balanced for enrobing. A second cream dose fills the remaining cavity around the nut. The deposit pattern is chosen to avoid trapping air, often by laying cream along the inner wall and then finishing the center volume. Air pockets can collapse later and create dents that show through the coating. Once filled, the opening is sealed. Depending on line design, sealing can use a wafer plug bonded with cream or a chocolate plug deposited to form a barrier. The seal must be flush so the sphere rolls smoothly and does not snag when entering the chocolate curtain. The filled spheres are conditioned and cooled before coating. This step firms the cream and stabilizes the wafer seam so the sphere does not deform under the weight of chocolate. Cooling is staged to avoid condensation because wafer absorbs moisture quickly. The aim is a firm center with a dry exterior surface, so coating adhesion is predictable. Chocolate coating is applied by enrobing. Spheres pass through a chocolate curtain that coats the surface. A wire belt supports the pieces, while excess drains away. Vibration under the belt can smooth the coat and help bubbles escape. Air knives can trim excess and control the final thickness. Thickness matters because it determines the bite balance and provides the adhesive layer for chopped nuts. Nut application happens immediately after enrobing while the chocolate surface is still tacky. The spheres roll through a bed of chopped hazelnuts or receive a nut shower from above while rotating on a moving bed. The goal is full coverage without clumps. Feed rate and bed depth are tuned so nuts embed into the chocolate rather than merely resting on top. Too rapid setting causes poor embedment and later shedding. Too slow setting allows nuts to slide and create bare patches. Cooling tunnels lock the structure. The first zone sets the chocolate surface quickly so the nuts stop moving and coverage becomes fixed. Subsequent zones cool more gradually, so cocoa butter crystals form in the stable state and contraction stress stays low. Proper cooling prevents cracks around nut peaks and keeps the surface gloss stable. During this time, the internal cream continues to firm as its fat phase crystallizes. The wafer remains protected because the cream and chocolate act as moisture barriers once set. After cooling, loose nut fragments are removed by gentle air brushing or screening so wrappers remain clean. Inspection checks look for incomplete coverage, deformed spheres, and weight anomalies that indicate missing nuts or underfill. Defective pieces are removed before wrapping because once wrapped, they cannot be visually corrected. Each sphere is then seated into a paper cup. The cup is a mechanical protection layer that reduces abrasion and keeps nut pieces from rubbing off during high-speed handling. The cupped spheres enter foil wrapping. Foil is formed around the piece and crimped into a tight seal. Tension and fold geometry are tuned so foil conforms around the textured surface without tearing and without compressing the sphere. Wrapped pieces are collated into trays where each pocket prevents movement. Trays are inserted into cartons, and cartons are closed and case-packed. Smarties are engineered from the outside in because the crunchy shell is built first as a process target, and the chocolate center is engineered to survive the shell growth cycle without deformation. The manufacturing line begins by defining the core size and density that the shell system can coat predictably. Chocolate ingredients are assembled into a fat continuous suspension where sugar and milk solids are dispersed in cocoa butter. The mass is refined until particle size is below the gritty threshold. Conching then stabilizes flow by fully wetting particles with fat and driving off residual moisture that would thicken the chocolate later. Tempering follows, so cocoa butter crystallizes into a stable form. Stable crystals matter because the center must stay firm while tumbling for long periods during shell building. Centers are formed as small lens-shaped pellets with tight mass control. Tempered chocolate is metered through deposit heads into shallow cavities or onto a cooled belt. In cavity forming, molds are vibrated so air bubbles rise and the surface levels, then the pieces are cooled until they release cleanly. In belt forming, deposited portions are shaped by calibrated rollers that control diameter and thickness. Regardless of our method, the key outcome is uniform geometry. Uniform geometry means each piece rolls the same way in the panning drum, which is what keeps shell thickness uniform. Fresh centers are conditioned before coating. Conditioning holds them at a temperature where they are hard enough to resist dents, yet not so cold that rims chip. This temperature window also prevents surface condensation. Any surface moisture would disrupt the first shell layers and create rough adhesion points. Conditioning tunnels use controlled air, so the center surface is dry and stable. Shell growth begins in rotating pans or perforated drums, where centers form a rolling bed. Drum speed and fill depth are tuned so pieces cascade and roll rather than slide. Rolling exposes every surface evenly to spray and drying air. Sliding produces flats and uneven build. The mechanical motion is therefore treated as a process variable equal in importance to syrup composition. The first shell layers are designed as an adhesion, bridge between chocolate and sugar. A very light sugar syrup is atomized and applied in short pulses. Droplet size is kept fine, so the film spreads thinly and does not pool. Immediately after spraying, dry air flows through the bed to evaporate water and initiate crystallization. These early layers must set fast enough to prevent pieces sticking together. They must also avoid adding enough water to soften the chocolate surface. Once adhesion is established, bulk build begins. A higher solid syrup is sprayed in measured increments. After each spray, fine sugar is often dusted onto the wet surfaces to absorb moisture and increase build rate. Airflow then removes water and drives crystallization through the new layer. The cycle repeats many times. Each cycle adds only a small amount of thickness, so stress stays low and cracks are avoided. Crystallization control is central to shell quality. If drying is too aggressive, the surface can crust while moisture remains inside the layer. Trapped moisture later causes pits and weak zones. If drying is too slow, the surface stays tacky and pieces form twins. Twin formation ruins shape and also disrupts bed dynamics. Air temperature, airflow rate, and humidity are adjusted together to match spray volume, so every layer reaches a stable set before the next spray. As the shell thickens, the process shifts towards surface refinement. Spray amounts per cycle are reduced and drying time per cycle is increased. Thin syrup films flow into micro valleys, left by earlier growth, and smooth the texture. The drum motion can be adjusted slightly as hardness rises. Slightly higher rolling energy helps round edges once the shell can withstand impacts. The adjustment remains limited because impacts still cause chipping at rims. Color is built as a surface system rather than a single dye addition. Color solutions are mixed to precise concentration and filtered so no particles clog spray nozzles. Color is applied in multiple light coats, with full drying between coats. Light coats build saturation evenly and avoid pooling in low spots. Heavy coats would produce blotches because the shell surface is not perfectly smooth at the microscopic level. Color timing is selected to keep shade bright. If color is applied too early, it becomes buried under later clear layers and looks muted. If applied too late, it can sit on a very hard surface and show uneven adhesion. Many lines introduce color when shell thickness is near target, but before final smoothing coats are completed. Then a few clear coats are applied to lock pigment and improve durability. Color runs are typically separated by batch to prevent cross tint. The pan and spray lines are flushed between colors. The reason is not only appearance. Cross tint also affects quality checks because shade drift can mask surface defects. Optical color measurement compares sample pieces to target shade and drives adjustments in pass count or concentration. After color, the shell receives a final hardening sequence. Clear syrup layers are applied in very small volumes and dried with longer residence. This tightens the crystal structure near the surface and improves resistance to scuffing. Hardness is tied to moisture, so the process targets a defined moisture endpoint rather than simply drying as much as possible. Overdrying can make shells brittle and prone to chipping during conveying. Moisture equalization follows. Even when the surface is dry, the inner shell can hold slightly different moisture. Equalization holds the product in controlled air, so gradients flatten. This reduces internal stress that can create fine cracks, and it stabilizes the surface for polishing. Polishing creates gloss and improves flow. Pieces move to a polishing pan where motion is gentler. A polishing agent is applied as a fine mist in tiny doses. The pieces tumble and the film spreads across the surface through repeated contact. The film fills micro pores and reduces friction. Reduced friction lowers scuffing during packaging and improves hopper flow. Polish application is controlled because excess polish changes mouthfeel and can reduce color brightness. The process applies small additions followed by tumbling time to distribute evenly. A brief rest can follow, so the film sets and the surface becomes dry to the touch. Sorting and screening remove defects created during tumbling. Vibratory screens remove fines and broken chips. Optical systems can reject twins, chipped pieces, and off-shade pieces. Size classification can remove pieces outside the diameter band because off-size pieces roll differently and appear inconsistent in packs. The finished Smarties then feed packaging. Conveyors are designed with low drop heights and smooth curves because impact can chip shells. Hoppers are steep and low friction to prevent bridging. Multi-head weighers portion target weights by combining small hopper dumps. Stable flow depends on low dust and stable polish. 4. Bag formats. Portions drop into vertical form, fill seal machines where film forms a tube, and seals are made above and below the drop. Seal timing keeps pieces out of the seal area. For carton formats, weighed portions drop into cartons and cartons close by, tuck or glue. In either case, packaging materials are chosen to limit moisture transfer because moisture changes shell crunch and can cause sticking. A high-volume Dunkin' Donuts line is built around delivering dough or batter to hot oil in the same condition every minute because frying fixes shape, crumb, and surface in seconds and leaves little opportunity to correct variation downstream. Ingredient conditioning starts the process. Flour is sieved to remove lumps and aerated for consistent hydration. Sugar is screened so crystal size stays stable and dissolves predictably in mixes. Salt and leavening are pre-blended, so distribution is uniform at low inclusion rates. Fats are tempered so their plasticity is consistent for dough systems or melted and cooled to a target temperature for batter systems. Eggs and dairy liquids are tempered because small temperature shifts change emulsion behavior and batter viscosity. Water temperature is selected to land the final dough or batter in a narrow temperature window. For yeast-raised donuts, the front end is a developed dough that must proof consistently. Flour enters a mixer and is hydrated with water and dairy liquids, while yeast is dispersed early, so fermentation is uniform. Mixing begins slowly to hydrate without dusting, then increases speed to develop gluten. Gluten development is tuned to a target elasticity that can trap gas but still sheet cleanly. Fat is added after initial gluten formation, so it softens the network without blocking development. Eggs and emulsifiers are incorporated in a controlled sequence, so they form a stable dispersion inside the dough rather than separating into streaks. Dough temperature is managed as a primary control variable. Mixing friction generates heat, so water temperature and mix time are adjusted to reach a target dough exit temperature. That exit temperature controls dough stiffness and yeast activity. The dough then enters a timed rest, where moisture equalizes and gluten relaxes. Relaxation reduces snapback in sheeting and improves cut accuracy, while early fermentation begins creating fine gas cells without fully expanding the dough. The rested dough feeds a divider and sheeter. Dividing stabilizes feed rate into rollers, so thickness remains steady across time. Sheeting reduces thickness through several roller gaps rather than one large reduction to avoid stress lines that later become weak points in the fryer. Gauge rollers lock the final sheet thickness, which becomes a main determinant of donut weight and final crumb thickness. Rotary cutters punch rings at line speed, cutting an outer diameter and removing the center plug. Cutter sharpness matters because dull edges compress the dough and create ragged rims that absorb more oil and brown unevenly. Scrap around the cutouts is lifted and returned to the dough stream at controlled ratios, because high scrap ratios increase working and shift gluten development. Cut rings move into proofing, where the dough expands to near final volume. Proofing is run at controlled temperature and humidity. Temperature sets yeast gas production rate, and humidity prevents a dry skin that would restrict expansion and cause blowouts. Proof time is tuned to reach a target volume and cell structure. Underproof yields dense donuts with limited lift. Overproof yields fragile donuts that collapse when moved or flipped in oil. For cake-style donuts, the line works with a chemically leavened batter rather than a fermented dough, so the objective is minimal gluten with uniform leavening dispersion. Dry ingredients are pre-blended, so chemical leavening and salt are evenly distributed. Liquid ingredients are blended separately, so eggs and fats emulsify before meeting flour. The streams combine and mix only long enough to hydrate flour and remove lumps, because overmixing develops gluten and produces tough donuts with irregular cracking. Batter temperature is held tightly because viscosity must remain stable for depositing. If batter is too thin, it spreads and loses ring definition when it hits oil. If too thick, it deposits unevenly and can trap air pockets that create voids. Depositing forms rings directly into the fryer for cake products. A depositor meters batter through shaped nozzles with timing synchronized to the fryer conveyor, so spacing is consistent. Deposit weight is controlled by pump stroke or timed flow. The batter must release cleanly from the nozzle and hold its shape long enough for the surface to set in oil. Frying is the setting step for both routes. Oil temperature, dwell time, and turnover are the controlling variables. When a donut enters oil, surface water flashes to steam, creating outward pressure that expands the structure and delays oil penetration during the earliest phase. Starch gelatinizes at the surface and forms a crust. Proteins coagulate and lock the structure. Browning reactions accelerate as the surface dries, creating the final color and flavor profile of the crust. Yeast-raised rings usually float and fry on one side first. Conveyor speed determines how long the first side sets before a turning mechanism flips the donut. Flip timing is critical. Flipping too early deforms the ring and creates flat spots. Flipping too late creates an overly thick crust on one side and uneven color. The second side fry completes structure set and balances moisture loss, so the donut does not warp. Cake donuts set more quickly because the batter begins as a suspension with chemical gas release and rapid heat penetration. Fry conditions are tuned so the surface sets at the right moment. If the surface sets too fast, expanding gases crack the crust and create blowouts. If the surface sets too slowly, the batter spreads and forms misshapes. Residence time and temperature are adjusted together to manage this balance. Oil management runs continuously because crumb fragments and batter fines burn, and darken the oil, changing heat, transfer, and color development. Filtration removes fines and keeps the oil clean. Oil is circulated to maintain uniform temperature across the fryer width and prevent striping. Controlled oil turnover keeps frying behavior stable, so the same dwell time produces the same color and oil pickup. As donuts exit the fryer, surface oil is removed immediately. Drain belts and vibrating conveyors shake off free oil, and air blowers strip oil from creases. This step is important because surface oil interferes with glaze adhesion and increases greasy feel. The donuts then enter cooling, where internal steam condenses, fats begin to crystallize, and the crumb firms. Cooling is staged to stabilize structure and prepare for finishing. Hot donuts are soft because fats are liquid and the crust is still plastic. As they cool, the crust becomes rigid and the interior moisture redistributes. Cooling airflow is controlled so the surface does not dry too fast, which would create a tough crust that flakes under glaze. Cooling also prevents packing too warm, because warm donuts release moisture into packages and soften coatings. Glazing and icing are applied in controlled viscosity windows. A classic sugar glaze is mixed to a defined solids level and held warm enough to flow as a thin film. Donuts pass under a glaze curtain or are dipped, and the excess drains as they travel on a setting conveyor. As water evaporates, the glaze crystallizes into a smooth shell. Chocolate or fat-based icings are heated to a target flow temperature and applied by curtain or dipping, then set by cooling so the fat network solidifies without cracking. Powdered sugar or cinnamon sugar finishes are applied while the donut surface still has slight warmth and tack. The donuts pass through a shower or drum that distributes powder evenly, and screens recover excess. Toppings are applied during the short tack window before coating set. Feeders meter sprinkles or nut pieces at a rate synchronized to belt speed, so coverage stays uniform without clumps. Filled donuts at an injection step after cooling reaches a firm but pliable state. Fillings are prepared to a pumpable viscosity that holds shape without leaking. Multi-needle injectors penetrate at controlled depth, and piston strokes deliver consistent doses. Needle retraction timing is coordinated to reduce backflow and surface smearing. If a side fill format is used, a controlled slit is cut, and a nozzle deposits filling into the pocket. Then the product passes through a brief set zone, so the filling surface stabilizes. Packaging is designed around protecting finishes and managing moisture exchange. Donuts intended to stay soft use barrier materials that reduce moisture loss. Donuts with a crisp shell need packs that prevent moisture gain that would soften crust and glaze. Cartons and clamshells protect toppings from abrasion and reduce contact marks, while flow wrap provides strong moisture control but requires the surface to be fully set to avoid smearing. Seal temperature and dwell are tuned so seals close without heating the donut enough to soften coatings. A Chick-fil-A style breaded chicken fillet is produced by turning trimmed poultry breast into uniform portions, conditioning the meat so it stays juicy after cooking, applying a controlled flour and batter system that bonds tightly, setting the coating quickly in hot oil, then chilling and packaging so every fillet reheats with the same crust and bite. Production starts with raw poultry arriving chilled and moving into size reduction and standardization. Breast meat is trimmed to remove thin tails and ragged edges that would overcook and create hard spots. The trimmed pieces are sorted by weight band so the forming line can hold a tight portion range. Consistent portion mass is a core control because fry time and internal temperature rise rate depend on thickness. The meat is then conditioned to stabilize moisture, retention, and texture. A measured solution is prepared from water, salt, and functional ingredients that improve binding and reduce purge. This solution is mixed to a defined concentration and held cold so it does not warm the meat. The solution is introduced to the meat by tumbling or by injection followed by tumbling. Tumbling cycles alternate between rotation and rest, so the solution distributes through muscle fibers without tearing them. Vacuum tumbling is often used because removing trapped air improves uptake consistency and reduces voids that can appear as soft pockets after cooking. The endpoint is judged by pickup percentage and by uniform surface tack rather than by extended mixing time. Once conditioned, the meat is portioned into fillet shapes. If whole muscle fillets are used, they are pressed to a consistent thickness using calibrated rollers. Pressing is gentle and aims to widen and even the piece without shredding. Thickness control matters because a thick center can remain undercooked when the crust looks done. If formed fillets are used, the meat is ground coarsely and then shaped in a forming machine. But a classic sandwich fillet format typically relies on whole muscle thickness control rather than full comminution. After shaping, the fillets pass through a brief chill stage. Chilling firms the surface proteins and improves handling so the pieces do not smear when they enter the coating system. Chilling also stabilizes the pickup behavior of the next layers because warmer surfaces thin the batter and increase coating variability. The coating system is built as a multi-step adhesion stack. The first layer is a pre-dust, usually a seasoned flour blend that absorbs surface moisture and creates a dry interface. Pre-dust is delivered as a curtain or bed where fillets tumble and roll so all surfaces are covered. Excess pre-dust is removed by gentle shaking because too much dry flour creates thick patches that later detach. After pre-dust, the fillets enter a batter stage. The batter is mixed in tanks that maintain solid suspension and viscosity. Viscosity is monitored because it determines coating thickness and how the batter bridges surface contours. Batter temperature is controlled because warm batter flows too thin and produces weak coating, while cold batter thickens and creates ridges. The fillets pass through a batter waterfall or immersion where every surface is wetted. Air knives can remove excess and set a uniform film thickness. Breading follows immediately while the batter is still wet. Breading is usually a seasoned flour system with a defined particle size distribution. Some formats use a mix of fine flour and larger crumb to create a textured crust. The fillets travel through a bed of breading while top belts press lightly to embed particles. This compression step is critical because it turns loose surface flour into a mechanically locked layer that will survive frying and later handling. Excess breading is removed so the crust is thick but not clumpy. If the target crust requires a distinctive craggy surface, the line can use a second batter and breading pass. The first pass builds the base and the second pass builds height and texture. Each pass is tuned so the coating does not become so heavy that it insulates the meat and slows cooking. After breading, the fillets enter a short setting zone before frying. This can be a brief rest on a belt that allows the batter to hydrate the dry breading and form a cohesive paste at the interface. Hydration improves adhesion and reduces blow-off in the fryer. The rest time is short because the coating must not become wet enough to smear. Frying is the structure setting step. Fillets enter a continuous fryer where oil temperature and dwell time are tightly controlled. The fillets are held under oil by a top belt so they cook evenly and do not float and curl. As the fillet enters oil, surface water flashes to steam. That steam creates outward pressure that expands the coating slightly and forms pores. Starches in the batter gelatinize and then begin to dry into a rigid network. Proteins in the batter coagulate and lock the crust shape. Oil temperature is chosen to set the crust quickly while allowing heat to penetrate the meat at a controlled rate. If oil is too hot, the crust darkens before the center reaches the target internal temperature. If oil is too cool, the crust sets slowly, absorbs more oil, and becomes heavy. Dwell time is set by belt speed and fryer length. Bed loading is controlled because overcrowding reduces oil circulation and causes uneven color. Oil management runs continuously because breading fragments break off and will burn if not removed. Filtration systems remove fines and keep the oil clean. Circulation keeps temperature uniform across the fryer width. Fresh oil makeup maintains quality so heat transfer and browning stay consistent. At fryer exit, surface oil is removed by vibration and air stripping. Removing surface oil reduces greasiness and improves how the fillets package and reheat. The fillets then enter a cooling stage. Cooling stabilizes the crust and lets internal steam pressure fall gradually. If cooling is too fast, the crust can contract and separate slightly. If cooling is too slow, residual heat can soften the coating and reduce crispness. From here, the process can diverge depending on distribution format. For a chilled product, the fillets are cooled rapidly to a target core temperature and held under controlled conditions. For a frozen product, the fillets enter an individual quick freezer. The freezer uses high-velocity cold air to freeze quickly and preserve crust porosity. Rapid freezing forms smaller ice crystals and reduces moisture migration that would soften the crust later. The pieces are spaced so they freeze individually and do not stick. After freezing, the fillets are screened and inspected. Broken coating fragments are removed because they increase crumbs in the package and can burn during reheating. Size and weight checks confirm portion control. Optical systems can reject misshapes and incomplete coating. Metal detection can be placed after freezing when product flow is stable. Packaging begins with portioning. Multi-head weighers or counting systems assemble target weights for bags or cases. Drop heights are minimized because frozen breading can chip and create fines. Bags are formed from barrier film that limits moisture exchange. Moisture control is crucial because the crust will lose crisp potential if it picks up moisture in storage. Seals are made with controlled heat so the film closes without wrinkles. Seal areas must remain clean because crumbs can interfere with seal integrity. For food service formats, the fillets are packed into lined cases with internal bags. Case fill patterns are chosen to reduce compression on lower layers. Cases are sealed and coated. Pallet stacking is designed to avoid crushing that would fracture crust. Storage temperature stability prevents freeze-thaw cycles that create ice crystals on the crust and degrade reheating performance. The final product performance is engineered into the factory steps. Meat conditioning sets moisture retention, so the fillet stays juicy after a high heat finish. Pre-dust and batter create a bonded interface so the crust does not slide off when bitten. Breading particle size and compression set the surface texture. Fry temperature sets pore structure and crust rigidity. Cooling and freezing preserve that structure. Packaging maintains low moisture exchange so the crust can crisp again during final cooking or reheating. A McDonald's-style hamburger is manufactured by turning beef trim into uniform patties that cook the same way every time, producing buns that stay soft yet resilient after freezing and toasting, then portioning and packaging each component so it can be assembled rapidly with consistent texture. Beef patty production starts with raw trim selection and temperature control because fat level and grind behavior determine bite and shrink. Beef arrives as chilled trim in defined lean-to-fat bands. The trim is inspected for hard connective pieces that would create tough spots and for excessive surface fat that would smear during grinding. Trim is kept cold from the start because warm fat smears into a paste, which causes dense patties and poor cook texture. The trim enters a coarse grinding stage first. Coarse grinding breaks the meat into uniform chunks without turning it into an emulsion. This is done through a grinder plate with larger holes, so particle definition is preserved. The coarse ground meat then moves to blending, where multiple trim lots are combined to hit a target fat percentage. Blending uses paddles that fold the meat rather than whip it, because air incorporation and overworking change density and can create voids. After blending, the meat is ground again through a finer plate to create the target particle size distribution. Particle size affects how the patty binds and how it releases juices. Too coarse yields a crumbly patty that breaks at the edges. Too fine yields a tight, rubbery bite. Grind temperature is monitored continuously because friction can warm the meat. If temperature rises, the line slows or adds colder meat to keep the mix in range. The blended grind is moved quickly to forming. Forming turns the loose ground meat into patties with a fixed diameter, thickness, and mass. A patty former meters meat into a cavity and compresses it to a set density. Compression must be strong enough to make the patty hold together during freezing and handling. Compression must not be so strong that the patty becomes dense and loses its characteristic bite. Formers often imprint a pattern on the surface. The imprint increases surface area and helps heat penetrate evenly during cooking. Weight control is enforced at the forming head. Portioning is measured by volume with density control or by mass flow with feedback. Tight weight control is important because cook time is fixed in high volume systems, so patties must reach target internal temperature within the same dwell. Patty thickness control is equally critical because a thicker patty heats slower and will be underdone when a thinner one is correct. Immediately after forming, patties enter a rapid freezing step. Freezing locks the shape and prevents patties from sticking together. Individual quick freezing is used with high velocity cold air. The patties travel on a belt through a tunnel where cold air freezes the surface quickly first, then drives the core down to the target temperature. Rapid freezing forms smaller ice crystals and preserves texture better than slow freezing, which can create larger crystals that damage muscle structure. Patties are then separated, counted, and stacked into interleaved layers. Interleaving uses paper or film sheets between patties to prevent adhesion and simplify later separation. Stacking pressure is controlled so patties do not deform. The stacks are bagged or boxed in a way that limits moisture exchange and protects edges from chipping. Metal detection and weight verification typically occur after freezing when product flow is stable and consistent. The bun is produced on a separate bakery line, built around controlling softness, resilience, and freeze-thaw stability. Flour is sieved and blended to a target protein range because gluten strength controls how the bun holds up to toasting and compression. Sugar and salt are metered precisely. Yeast is staged as a controlled addition because fermentation rate must match line speed. Fats and emulsifiers are included to soften crumb and extend softness after freezing. Water temperature is controlled because dough temperature drives fermentation speed and dough handling. Mixing develops gluten to a defined endpoint. The dough must be strong enough to trap gas and rise, but not so strong that the bun becomes chewy or tough. Mixing begins with hydration and then transitions into higher energy kneading until the dough reaches a smooth, elastic state. Dough temperature is checked at discharge because mixer friction can warm the dough and accelerate fermentation. If dough exits too warm, proof times shorten and the process becomes unstable. After mixing, dough is rested and then divided. Dividers. Portion dough into equal pieces by weight. Portion weight directly determines bun diameter and height. Divided pieces are rounded to create surface tension, which supports a uniform shape during proofing. Rounded dough balls then rest briefly to relax so they can be shaped without tearing. Shaping forms the final bun geometry. Dough balls are flattened slightly and placed onto baking trays or oven bands. Proofing follows in a warm, humid environment. Proof temperature controls yeast activity and gas generation. Humidity prevents skin formation, so the bun can expand smoothly. Proof time is tuned, so buns reach a target volume and internal cell structure. Underproof yields dense buns with low softness. Overproof yields weak buns that collapse and wrinkle. Baking sets structure and dries the bun to a controlled moisture endpoint. Tunnel ovens run zoned heat, so the surface sets and the crumb cooks without excessive crust hardness. Early oven zones drive oven spring as trapped gas expands. Mid zones gelatinize starch and coagulate proteins to fix the crumb. Later zones develop a light crust color and finish internal moisture reduction. The bun must not be too dry because it will feel stale. It must not be too wet because it will collapse and compress poorly. After baking, buns cool on conveyors with controlled airflow. Cooling sets the crumb as fats crystallize and moisture redistributes. Slicing is done after cooling reaches the right firmness. Slicers cut buns horizontally with blades that maintain a consistent hinge or full separation depending on format. Slice depth is controlled because it affects later toasting behavior and bun strength during assembly. Sesame seeding, if used, is applied either before baking for adhesion or after with an adhesive wash depending on equipment design. For high volume distribution, buns are often frozen. Freezing protects softness and allows stable inventory. Buns enter a freezing tunnel where surface is frozen quickly to maintain shape. Packaging then seals buns in bags with barrier properties that limit dehydration. Bag seals must be strong because freezer burn dries bun surfaces and changes toasting behavior. Cheese slices, pickles, onions, and sauces are produced as separate streams with their own controls. But in the context of assembly readiness, the main requirement is portion uniformity and stable handling. Cheese is portioned into slices with tight thickness. Pickles are cut to consistent thickness, so acidity and crunch are predictable per unit. Dehydrated onions are produced by slicing onions and drying them to a low moisture level, then sizing flakes, so rehydration in the final product is consistent. Sauces are mixed as emulsions with defined viscosity, so dispensing systems deliver repeatable weights. Packaging and logistics are treated as part of the production system because the end product depends on thaw and cook behavior. Frozen patties are boxed in counts that match downstream loading systems. Boxes are designed to stack without crushing product. Buns are packaged to reduce moisture loss and protect shape. Temperature stability through storage is critical because freeze-thaw cycles create ice crystals that damage texture and cause condensation inside packs. The final operational transformation happens at the cooking line, where frozen patties are separated and cooked on a clamshell grill. The clamshell grill is engineered for repeatability. Patties are loaded onto a lower hot platen and then a top platen closes to contact both sides. Contact cooking on both sides reduces cook time and ensures uniform heat penetration. Time and platen temperature are fixed, which is why patty thickness and mass upstream must be consistent. The surface imprint on the patty increases contact and helps fat render evenly. The defining feature of a crispy cream-style ring donut is the thin, tender crust and airy interior that come from a dough that is proofed to a narrow endpoint, fried with a controlled flip, then glazed while the surface is still warm enough to accept a uniform film without soaking. Everything is organized around the proof to fry handoff, so the line is built to keep dough pieces moving continuously from cutting to proofing to oil without waiting. The dough system starts with flour and liquid staged to produce a consistent final dough temperature. Flour is sieved to remove lumps and to stabilize flow into the mixer. Sugar is screened so crystal size does not vary significantly because sugar affects both fermentation rate and browning. Salt is weighed precisely to control dough strength and yeast activity. Yeast is prepared as a dry addition or slurry, so it disperses evenly. Fat is tempered so it blends smoothly without streaking. Water and dairy liquids are tempered because final dough temperature is one of the strongest predictors of proof time. Mixing builds a gluten network that can expand without tearing. The mixer begins at low speed to hydrate flour and incorporate yeast and sugar uniformly, then increases speed to develop gluten to a target elasticity. The target is not maximum strength. The dough must be strong enough to hold gas during proofing and frying, but extensible enough to sheet cleanly and cut without shrink. Fat is introduced after initial gluten development, so it softens the network rather than blocking formation. The mix endpoint is judged by dough smoothness and elasticity and by temperature. If the dough exits too warm, it will ferment too fast and become sticky on rollers. If too cool, it will be tight and resist expansion. After mixing, the dough enters a short rest to equalize moisture and relax gluten. Relaxation reduces snapback in sheeting, which is essential for ring accuracy. During this rest, early fermentation begins creating small gas cells. The rest is timed so the dough remains workable and does not overexpand before forming. Forming begins with sheeting. The dough passes through a series of reduction rollers that gradually decrease thickness. Large reductions are avoided because they create stress lines that show up as weak spots during frying. Gauge rollers at the end set the final sheet thickness, and that thickness becomes a primary determinant of donut weight and final crumb thickness. The sheet then enters rotary cutting, where an outer ring and an inner hole are cut in one motion. Cutter sharpness is critical because dull cutters compress the edges and create ragged rims that absorb more oil and brown unevenly. Scrap dough around the cutouts is lifted and recycled at controlled ratios because heavy recycling increases work input and changes dough strength. Cut rings are transferred onto proofing screens or belts with minimal distortion. Transfer height is kept low, and the dough is supported so it does not stretch. Stretching changes ring thickness and causes uneven expansion. The rings then enter the proofer, which is essentially a controlled fermentation chamber that raises the dough to near final volume. Proofing conditions are set to achieve rapid, even expansion without forming a surface skin. Temperature controls yeast activity. Humidity prevents the surface from drying and sealing, which would trap expanding gas and cause blisters. Proof time is tuned so the ring becomes light and inflated, yet still strong enough to be moved and flipped in oil. Underproof produces dense donuts with thicker crust and less lift. Overproof produces fragile rings that collapse when they hit the fryer or when they are turned. The fryer is designed to set the structure quickly while preserving a thin crust. Oil temperature is held in a narrow band and monitored continuously. When proofed rings enter the oil, surface water flashes to steam, creating outward pressure that expands the ring further and helps delay oil penetration in the earliest seconds. Starch gelatinizes at the surface and forms the initial crust. Proteins coagulate and lock structure. As the surface dries, browning begins and color develops. Rings typically fry one side first while floating. Conveyor speed sets the dwell on the first side, then a turning mechanism flips the ring. Flip timing is a major control because the first side must be set enough to support the ring during rotation, but not so overcooked that it becomes thick and dark. After the flip, the second side fry completes structure set and balances moisture loss. The total fry time is tuned to yield a pale, thin crust that remains tender rather than thick and crunchy. Oil management is continuous because crumbs and fragments break off and burn, darkening oil and changing heat transfer. Filtration removes fines. Oil circulation maintains uniform temperature across the fryer width. Fresh oil addition and controlled bleed maintain quality, so color remains consistent from hour to hour. Stable oil behavior is essential because even small changes in heat transfer shift crust thickness and glaze pickup. As rings leave the fryer, surface oil drains immediately. Drain belts and brief vibration shake off free oil. Removing surface oil matters because it affects glaze adhesion and prevents greasy patches that repel glaze. The donuts then move onto a short cooling conveyor, but the cooling is not intended to fully cool them. It is intended to bring the surface into the glaze window. Glaze is applied while the donut is still warm. The glaze is a sugar solution or suspension mixed to a defined solids level. Solids level determines film thickness and set speed. The glaze is held warm enough to flow smoothly, but not so hot that it becomes too thin. Donuts enter a glaze waterfall or curtain where glaze coats the surface. Excess glaze drains as donuts travel on a belt. The warm donut surface helps the glaze spread evenly and then set. If donuts are too hot, glaze becomes excessively thin and runs off, leaving a patchy coat. If too cool, glaze sets too quickly and creates uneven coverage and a grainy texture. After glazing, the donuts move through a setting zone where glaze crystallizes. Airflow here is controlled because strong airflow can dry glaze too fast and create a rough finish, while weak airflow can leave glaze tacky and prone to sticking in cartons. The objective is a smooth, thin glaze shell that remains slightly delicate and glossy. For filled products, filling is typically done after the donut has cooled further and the crust has stabilized. A controlled injection system uses needles to place a measured dose of filling. Filling viscosity is tuned, so it flows through needles without tearing the crumb, and then holds shape without leaking. Needle depth and dose volume are controlled, so filling is distributed without blowouts. If a cut and fill format is used, a slit is made and a nozzle deposits filling into the cavity, then the surface is finished and allowed to set. Chocolate icing or other coatings are applied after glazing or instead of glazing depending on format. These coatings are typically fat-based and set by cooling rather than crystallizing like sugar glaze. Coating temperature and viscosity determine thickness and surface smoothness. Toppings are applied while the coating is tacky so they adhere before the surface sets. Packaging and handling are built to protect the glazed surface, which can mark easily. Donuts are typically loaded into cartons that prevent stacking pressure on the glaze. Carton loading uses guides that minimize contact with the top surface. If the product is individually wrapped, the donuts must be fully set and cooled to avoid condensation inside the wrap and to avoid smearing. Wrap films are selected to manage moisture because donuts dry out quickly if exposed to air. Snickers manufacturing can be understood from the cutter backward because the entire line is built to deliver a layered slab that is firm enough to slice cleanly, stable enough to ride through a chocolate curtain, and uniform enough that every bar finishes at the same weight. At the cutter, the slab must present a flat top surface, a consistent total thickness, and a predictable resistance to the knife. If the slab is too soft, caramel smears and drags, nuts dislodge, and edges tear. If the slab is too hard, the caramel fractures and the nougat can crack into ragged faces that later create coating voids. The plant therefore shapes and cools each layer so the combined slab reaches a narrow cut window before portioning begins. The slab is built on a continuous belt. The bottom layer is aerated nougat. Nougat begins with two inputs that are prepared separately so they can be combined without collapsing the bubble structure. A cooked syrup that defines solids and elasticity, and a foam phase that carries metered air. Syrup cooking starts with sugar and glucose syrup streams that are metered into a cooker and concentrated. The cook endpoint sets the moisture level in the final nougat. A higher moisture syrup yields a softer nougat that can slump under the caramel layer. A lower moisture syrup yields a tighter nougat that becomes chewy and resists cutting. The cooker is operated to a precise endpoint, and the syrup is delivered forward at a controlled temperature so it strengthens foam but does not scorch it. The foam phase is produced from a protein solution. The solution is mixed to a defined concentration and fed to a continuous aerator. Air is metered in, and shear is applied to create small, uniform bubbles. Bubble size distribution matters because large bubbles collapse and create voids, while small bubbles create a smooth, light texture. Density is measured continuously because density is the direct control for nougat weight and bite. If density drifts, the finished bar weight drifts. Syrup and foam merge in a continuous mixer designed to fold rather than whip. Folding distributes syrup through foam without breaking bubbles. Syrup heat partially sets the protein films and locks the microcell structure. Fat is injected as a thin stream to soften bite and reduce stickiness. Emulsifiers can be added in small doses to stabilize the air-fat sugar system and improve flow at the depositor. The mixed nougat exits as a warm, aerated mass with controlled viscosity. Nougat is deposited onto the moving belt as a continuous slab. A spreader head lays down a wide band, and gauge rollers set thickness. Thickness control is critical because it defines the core height and influences later cooling time. The slab enters a cooling tunnel with staged zones. Early zones firm the surface enough to support caramel deposition. Later zones remove heat more gradually so the interior firms without forming a brittle skin. The target exit condition is a nougat slab that is firm but still receptive at the surface so caramel can bond. Caramel is prepared in a separate stream because it requires different cooking and different set behavior. Sugar and glucose syrup are cooked with dairy components to develop caramel notes and reach an elastic solids endpoint. The endpoint determines whether caramel behaves as a clean sheet or as a smear. Too low solids and caramel drags on knives. Too high solids and caramel fractures, especially when nuts create stress points. Fat is added to smooth the matrix and reduce tack. The caramel is cooled to a working temperature where viscosity is stable for deposition and held in jacketed tanks with gentle agitation to prevent skin formation. Peanuts are prepared as a topping stream that must spread evenly and remain dry. Roasted peanuts are screened to remove fines and broken pieces. Fines create dust and uneven coverage. Oversized pieces create peaks that cause thin chocolate spots later. The peanuts are cooled after roasting so they do not warm the caramel surface and change tack behavior. They are stored in dry conditions so they flow freely through spreaders. Layering begins when the nougat slab reaches the caramel station. Caramel is deposited as a continuous layer using a slot head. A leveling bar spreads it to uniform thickness. Temperature matching is essential. If caramel is too hot, it softens the nougat surface and creates a weak interface. If too cool, it does not fuse and can delaminate later. The line targets a condition where caramel wets the surface slightly and then begins to set as it moves forward. Immediately after caramel deposition, peanuts are applied. A spreader distributes nuts across the full width at a controlled mass flow. Distribution must be uniform, so every bar receives a similar nut density. A light pressing station can embed nuts slightly into caramel to improve mechanical lock. Pressing is controlled to avoid crushing nuts and to avoid squeezing caramel sideways, which would create thick edges and thin centers. After nut application, the slab enters a conditioning zone. This zone firms the caramel layer enough for cutting and locks nut position, so nuts do not slide when the slab is later accelerated. Cooling is staged to avoid differential contraction between nougat and caramel, because differential contraction can cause the slab to curl. Curling leads to uneven coating thickness and cutting errors. The slab is held flat by belt support, and cooled to a target firmness. Edge trimming removes uneven edges where thickness variation is most common. Trim is collected for controlled rework streams. The main slab then enters lane cutting. Rotary knives slice the slab into long lanes of constant width. A crosscutter then slices lanes into bar lengths. Knife timing is synchronized to belt speed to maintain consistent weight. Knife surfaces are managed to reduce caramel buildup that would tear edges. Clean edges are important because ragged edges trap air under the chocolate curtain and cause voids. The cut bars are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfer points are designed with minimal drop height because impact can dislodge nuts and dent nougat. A brief pre-chill can be used to firm the surface and improve chocolate coverage. Pre-chill is balanced so the bars do not become so cold that condensation forms when they enter warmer chocolate equipment. Chocolate coating is prepared and held in a tempering loop. Chocolate is melted and filtered to remove unmelted fragments. Tempering creates a stable seed crystal population through controlled cooling and reheating. Working temperature is maintained tightly because viscosity defines curtain thickness and coat weight. Viscosity that drifts too high produces heavy coatings and thick feet. Viscosity that drifts too low produces thin coatings and exposed corners. Enrobing coats the bars with a top curtain and a bottoming system. The top curtain covers the top and sides. The bottoming system coats the underside, sealing the bar and protecting caramel from exposure. Excess chocolate drains through a wire belt. Air knives smooth the surface and control foot thickness. Air knife settings are tuned so they remove excess without exposing nut peaks at corners. If a top drizzle pattern is required, it is applied immediately after enrobing while the surface is still tacky. A stringer deposits thin lines that bond to the base coat. The bars then enter the cooling tunnel. Cooling is staged to set the chocolate and preserve surface quality. The first zone sets the surface quickly so the coating does not slump and nuts do not shift. Subsequent zones cool more gradually to promote stable cocoa butter crystals and reduce bloom risk. Tunnel humidity is controlled to prevent condensation that would cause sugar bloom and dullness. Bars exit the tunnel at a temperature suitable for wrapping with a coating hard enough to resist scuffing. After cooling, inspection checks coating coverage, shape, and weight. Vision systems detect exposed edges and coating voids. Weight checks confirm portion control across cutting and coating. Bars outside tolerance are diverted. Chocolate rework is remelted and returned upstream. Nougat and caramel rework is handled separately because their aeration and moisture differ from fresh streams. Wrapping begins once bars are fully set. Flow wrappers form film around each bar and seal it with controlled heat and dwell time. Film tension is controlled to avoid scuffing the coating. Coating is applied for traceability. Wrapped bars are collated into multi-packs or cartons, then case packed. Lay's-style potato chips are manufactured by controlling three things more tightly than anything else: slice geometry, surface starch, and oil temperature. When those three are stable, the process reliably turns raw potatoes into thin, brittle chips that drain cleanly, accept seasoning evenly, and stay crisp inside a sealed bag. The line is easiest to follow from the seasoning drum backward because seasoning performance tells you whether the upstream steps produce the right surface. Chips that are too wet reject powder and clump. Chips that are too dry fracture into excessive fines. Chips that carry excess surface oil feel greasy and carry seasoning unevenly. The factory therefore builds chips so they exit the fryer with a narrow moisture and oil window before they ever reach flavor application. The final steps start at de-oiling. Chips exit the fryer on a mesh conveyor and immediately pass over vibrating drains. Vibration shakes off free oil while the chips are still hot. and rigid enough to tolerate movement. Air knives or blowers can strip oil film from the surface and from curled edges. This is not a cosmetic step. Excess surface oil can cause seasoning to clump and can also migrate into the bag headspace, increasing the perception of greasiness. De-oiling settings are tuned so oil is removed without cracking the chips into fragments. From de-oiling, chips flow into a rotating seasoning drum. The drum provides gentle tumbling, so every chip surface is exposed. Seasoning is dosed as a fine powder or a blend and is metered by mass flow to match chip throughput. Adhesion relies on a thin oil film that remains on the chip surface. Too much film causes heavy seasoning pockets. Too little film yields bare chips. Drum speed and fill level are adjusted so chips roll rather than slide, because rolling distributes seasoning and minimizes breakage. A short dwell time allows seasoning to distribute fully without grinding chips into fines. Immediately after seasoning, chips move toward packaging, but they first pass through screening. Screens remove small fragments and fines produced by slicing and frying. Removing fines improves bag appearance and also prevents seals from being contaminated by dust. Fines also absorb more oil and can go stale faster, so their removal improves consistency. Packaging begins with portioning into bags using multi-head weighers. Chips are lightweight and irregular, so the weigher uses multiple small hoppers and selects combinations that hit target weight. Drop paths are designed to reduce breakage. Bags are formed from barrier film that resists oxygen and moisture transmission. Nitrogen flushing is commonly used to displace oxygen and to create headspace that cushions chips. The bag is sealed with heat and pressure. Seal parameters are tuned so seals hold without wrinkles that would leak. All of those downstream steps assume chips arrived with the correct structure, which is created in the fryer. Frying is not just cooking. It is a controlled dehydration process that forms a rigid, porous matrix. Chips enter hot oil and water at the surface flashes to steam. Steam leaves through the sliced surfaces, creating pores and crispness as moisture content drops. Oil temperature is held in a narrow band because it controls how fast water leaves and how much oil enters. If oil is too cool, chips stay in the fryer longer, absorb more oil, and remain flexible rather than crisp. If oil is too hot, the surface can brown before moisture leaves evenly, producing dark edges and fragile structure. Residence time in the fryer is controlled by conveyor speed and by chip bed depth. Bed depth matters because too deep a layer reduces oil contact and yields uneven color. Oil circulation is designed to keep temperature uniform across the fryer. Filters continuously remove crumbs and starch fragments that break off. Without filtration, crumbs burn and darken the oil, increasing dark specks and changing heat transfer. Oil turnover with fresh oil additions maintains consistent frying behavior over long runs. Before frying, slices go through a washing stage that controls surface starch. Freshly sliced potatoes release starch that forms a sticky film. If that film remains, slices stick together in the fryer and cook unevenly. The wash system uses flumes and sprays to remove free starch. Flow is tuned so slices separate without breaking. After washing, slices are dewatered on vibrating screens and with air knives. Removing surface water matters because water entering the fryer cools the oil locally and increases splatter and oil breakdown. Dewatering stabilizes fryer temperature and improves chip texture. Slice geometry is set at the slicer and influences every downstream step. Potatoes are fed into a high-speed slicer where a rotating blade cuts thin slices at a fixed thickness. Thickness is the primary determinant of crispness and color. Thinner slices cook faster and become very crisp, but can be fragile. Thicker slices cook slower and can remain slightly chewy if the fryer is not adjusted. The slicer uses sharp blades to create clean edges. Dull blades tear cells and create ragged surfaces that absorb more oil and shed more fragments. Many chip lines also apply slice sorting. A screen separates small fragments and slivers from full slices. Slivers fry faster and become darker, so removing them improves color consistency. Some lines also classify slices by thickness using optical measurement and divert out-of-range slices. Keeping thickness narrow allows fryer time and temperature to remain stable. The potato feed to the slicer is stabilized by upstream size grading. Potatoes arrive in bulk with variation in diameter and length. Large variations can cause feed surges and slicing inconsistency. A grader routes potatoes to appropriate lanes or rejects extremes. Feed hoppers and belts deliver a steady flow to the slicer, so blade load remains consistent. Consistent blade load produces consistent thickness. Raw potato preparation begins at receiving. Potatoes enter water flumes that transport them while removing stones and heavy debris in trap sections. Spray washers remove soil that would dull blades and discolor oil. Peeling is used on many lines. Abrasive peelers remove skin by rubbing against carborundum surfaces, while steam peeling can loosen skins quickly before mechanical removal. Peeling choice depends on product style. For classic thin chips, peeled potatoes provide uniform color and reduce dark spots. After peeling, potatoes are rinsed to remove peel fragments and then inspected by optical sorters that remove rotten spots and green areas that would fry dark and taste bitter. Temperature control begins early because potato temperature affects slicing and frying. Cold potatoes slice more cleanly and release less surface starch, but very cold potatoes can have higher reducing sugar levels from cold storage, which increases browning. The plant manages potato storage and tempering so raw potatoes arrive at a temperature that supports both slice quality and target color. Reducing sugar content is managed through raw material selection and sometimes through brief conditioning treatments. Potatoes with high reducing sugars brown too fast and produce dark chips. Wash and blanch steps are more common for fries than for chips, but some chip lines manage sugar through storage control and by blending lots. The goal is consistent color without relying on heavy downstream correction. After slicing and washing, the system focuses on gentle transport. Slices move through flumes and onto dewatering belts. The line avoids high drop heights because thin slices tear easily. Torn slices become fines and increase oil degradation in the fryer. Gentle transport reduces breakage and improves yield. The transition into the fryer is designed to avoid clumping. Slices are spread into a uniform layer before entering oil. Spreading can be done with distribution belts or vibratory feeders. A uniform entry layer ensures every slice sees similar oil contact and similar dwell time, producing uniform moisture removal and color. After frying, chips pass through a color sorting stage on many lines. Cameras measure chip color and eject overly dark chips with air jets. This stage compensates for occasional raw potato variability and fryer transient conditions. Sorting reduces the incidence of bitter dark chips in the bag and improves visual uniformity.